Joe Rogan Podcast. Check it out.
The Joe Rogan Experience.
Train by day, Joe Rogan Podcast by night, all day.
What's happening?
Hey,
How are you, sir?
how's it going, Joe? Good
Pleasure to meet you.
Yeah, thank you for having me here today. I appreciate it.
My pleasure. Well, as soon as I saw the subject, I was like, oh, yeah. Like, what are you doing?
Right. Advanced power and propulsion. Kind of been a passion of mine for the last 20-some-odd years. I suppose if I kind of look back through the annals of my life, right, I've been thinking about advanced power and propulsion ever since I was a teenager.
What do you think inspired that? Was it space missions? Did you look at it and go, I think we can do better? Like, what was it?
Well, you know, I grew up in Washington, D.C., and so I got a chance to spend a lot of time in the Air and Space Smithsonian. I don't know if you've ever had a chance
I haven't.
to go to that. But growing up in D.C., getting a chance to go to the Air and Space Smithsonian, I got to see all these awesome examples of people working together to try and accomplish amazing things, right? And you know, you might walk into the Air and Space Smithsonian and you just think about, wow, this is full of a bunch of stuff. But it's not just about the stuff, right? It's about the people that worked together to do all these amazing things, right? Like the Bell X-1 rocket. I mean, if you really want to go back, the Wright Flyer, right? That's something where two guys worked together that made bicycles for a living that decided to go create something that flew. And then in less than 50, 60 years from when they flew that Wright Flyer, right, we're putting human beings on the surface of the moon. And so all that really resonated with me as a kid, and I think tended to make me gravitate towards a technical field, although it wasn't a straight line, right? I'd like to say, I knew at an early age what my calling was and what I was going to do, but I bounced around for a little bit until I finally got on a path that, I really connected with. And so I think I knew very early on in my journey in university, right, when I was going and getting my degree, that I wanted to work in advanced power and propulsion. And so at that point, everything I did kind of worked towards how do I get the skills, how do I get the math and physics training that helps me kind of work in this domain? Because I was thinking about the idea of space warps very early on, right?
It's amazing that you were so focused so early. What a great head start. It's a huge advantage to know what you're really interested in at such an early age.
There were a few speed bumps along the way. We took a few detours, like any human, right? You're like, I don't know if I want to do this yet, right? So.
Yeah. Well, it is pretty extraordinary if you look at that number that you said, like from Orville Wright and Wilbur Wright to space travel, how quick that is.
Yeah.
And we think about in terms of ancient history, how long it took us to get to this point. And that kind of acceleration so rapidly inside of a lifetime to see just world-changing events and the internet all happening simultaneously, right?
Absolutely. There's another interesting story, right? So my background is I've got a PhD in physics and a master's in mechanical engineering. So I'm both a scientist and an engineer. So I have deep appreciation for both disciplines. But within the discipline of science, right? We just talked about the Wright Flyer and then going to the surface of the moon, and that's more of a kind of an engineering story. On the topic of science, think about E equals MC squared. You probably heard that or saw it on a coffee cup.
I don't really honestly know what it means. It's a theory of relativity.
It's theory of relativity.
I could say it to people like, come on, man.
Right. E equals MC squared.
Whatever. Explained it. Right? What is the theory of relativity?
So E equals MC squared, right, is an equation that relates energy to mass. If you were to take some modest piece of mass, say you've got some tidbits here, the mass that's in this pen right here. Mm-hmm. If you take the mass that's in this pen and you convert it to energy, that equation helps you understand exactly how much energy you can potentially release. And so that equation, why it might sound very humble, right? Oh, E equals MC squared. That's cool. But it had super big implications. And you just talked about how quickly things move. So let's talk about that for just a second. E equals MC squared. Einstein comes up with this equation, 1911. Somebody will look it up on the internet and correct me if I'm wrong. Comes up with the equation in 1911. They split the first atom in 1928, 1932 timeframe. I can't remember the exact timeframe. 1942, we had the first nuclear reactor underneath a squash court at University of Chicago. They did things very differently in the 1940s, Joe.
Under a squash
Yeah,
court?
right. Yeah.
Did they let the people playing squash know?
Who knows, right?
What happened to them? Are they X-Men now?
Yeah, right, exactly. That's the origin story. That's the Spider-Man origin story, right? So, yeah.
That's where Phoenix came from.
Yeah. Your friends tell you, I think I can hear the color blue now, right? So, yeah. So anyway, had the first nuclear reactor underneath the squash court in 1942, and then the Trinity test. That's the atomic bomb test in 1945. And so, in the span of just a few decades, we go from a cute coffee cup worthy equation to a paradigm shift in human existence, right? And that's without computers in the way we think of it. That's without machine learning and without AI. And so as we continue to move forward, right, we've got, if you think about everything we know in physics today, general relativity and quantum mechanics are kind of the two bookends of everything that we know. We're going to continue to expand our knowledge, and we will come up with new E equals mc squared kind of equations. But now we're equipped with computers, we're equipped with machine learning, AI, and so it's going to be exponential growth, right? So it'll be interesting to see how quickly we go from, hey, I have this new insight, found this funny thing in a lab, to, wow, it changes everything, how we do everything as a culture and community, right?
So there's several problems with the current propulsion systems, right? And the big one is like biological entities being able to absorb G-force, right? No matter if you super hyper engineer something and have it really crazy, but the things that we're seeing in the sky, the things that people describe, like Commander David Fravor, when he described that Tic Tac, that vehicle, that thing, whatever it was, that went from above 50,000 feet to sea level in a second. And shot off at insane rates of speeds. Biological entities can't survive that kind of G-force, we think.
Yeah, so I think in terms of a human ability to take G's.
Yeah, I should say human, not like tardigrades could.
Yeah, right. Yeah, so a human being can, trained human beings can take potentially up to 9 Gs.
Have you ever done that before?
I have not. Right?
I did it once with the Blue Angels.
Yeah.
I got to 7.5 Gs. It was bananas.
That's awesome.
I
bet that was an experience. Man.
Oh, it was.
Oh my! I am so jealous. Golly,
mad respect for those guys. Mad respect for those guys. Yeah. First of all, the biggest thing when you go to that area, like these guys are jacked. They're in like insane shape because you're literally forcing blood into your brain to tolerate the G-force.
Yeah.
So they have to hold on to their stick, their joystick, and they're going hoop, hoop, hoop. While they're flying, going through the canyons. It's bananas.
Yeah.
Like extraordinary.
Yeah.
So imagine a person being able to tolerate that on a regular basis and perform fine motor skill functions like pointing and aiming and shooting and all the crazy stuff that those guys are capable of doing.
Being able to think, and in some cases, if they're in combat, being able to make critical decisions. In some ways, what you're talking about, when you look at NASA's astronaut corps, right, as part of their regimen, they have to go up in T-38s on a regular basis to try and help train with the whole, how do you make decisions, right, when your life is on the line and the time is finite, right? So there's a whole aspect of this that's kind of geared towards keeping those portions of the brain trained and sharp, right?
Right, which is the best argument for AI taking over. When you hear about stories about these fighter pilots finding these objects in the sky that exhibit extraordinary capabilities and don't have all the signatures of traditional propulsion systems, what is your thoughts?
Generally, I tend to be agnostic to the topic. I have a lot of friends that are extremely interested in a lot of things that are out and about in the media and in the literature. But generally, I tend to be agnostic, and here's why. In everything that's currently out that people talk about and highlight, it's difficult for me to take the data and the evidence and then pull that into the work that we do in the lab with some of the different test devices we work with as we kind of explore the frontiers of where physics and propulsion might intersect. it's hard to take that and turn that into some kind of an action plan, if you will. So I'm certainly aware, like David Fravor, the experience that he had with, I think he calls them Tic Tacs, right? An amazing account. And there's multiple people that saw it, multiple platforms that saw it. And so to start with, right, I thought maybe there was a small chance that was just like we have stealth technology, right, where if you want to hide a plane, what if we had the ability to project something, right, through some mechanism where we could make people go where we wanted them to go, right? Because I know there's a technology that uses like two different lasers that triangulate a certain point in open air, and they put enough energy into a particular location that they ionize the air, and so it creates like a bright pixel. And so they use that to create three-dimensional displays that kind of look like they're just floating out in air. Now, they're not quite as big as what we saw described with the Nimitz encounter on the West Coast. So I thought for a little while maybe that might be something that we're seeing.
They can project plasma as well, right? Is that the same thing?
It's the same thing, right? So the two lasers intersect, they ionize the air, which creates a plasma.
And
right?
they can do this over long distances as well, right?
I don't know about long distances. I know they can do it over short distances.
Okay.
And so for a while there, I wondered if that might be something that could explain some of what
that makes sense.
What David Fravor and the group saw.
The only problem would be the radar, because I don't know if you wouldn't pick up that on radar, would you? Because it's not a mass, right?
So the plasma would certainly absorb a radar signal, right? Because it's gonna polarize any electromagnetic wave that tries to go through.
So it would show up.
It might. It might.
Would it be possible to make something that big, that's 20 feet long, out of that?
It's hard for me to imagine that.
Right.
But I think there's one piece of data that just came out in the last few weeks. I think David Fravor's Wingman Alex, I think her name is Alex Dietrich. I can't remember the name.
I think you're right. Something like that.
So she came out, and so in all the things associated with that particular encounter, right? One of the things I've been trying to figure out is how do they describe the specular surface of the Tic Tac, right? Because if it's these plasma pixels that I'm talking about that kind of creates a volumetric display, I would speculate it might be kind of a glowy looking thing. But I think Alex, in her account, described it as kind of a flat type of
like matte, yeah.
Yeah, so that kind of torpedoed my working theory. So, but again, while it's amazing and incredible, and it's something that people want to go think about and go try and collect more data, it doesn't help me do what I'm doing in the lab. And so I think I kind of keep, my eyes dart every once in a while over to that particular topic. Oh, what's that about? That's interesting. Right?
Yeah, I mean, I'm honestly agnostic as well. I bounce back and forth from being really excited about it to feel like I'm being duped all the time. Jamie and I talk about it all the time. I'm back in. And Jamie's back in, and Jamie will find something. He's like, I think I'm back in. How are you right now?
I'm looking through the article about the Navy laser that can do this. I'm trying to figure out how big the objects are that they can make move. But they're designed to trick heat-seeking missiles, so they got to be big enough for that. So they want to.
Okay, so they make a heat signature. So they trick the heat signature, which makes sense, right? Because they're plasma.
Yeah, it can from tens to hundreds of meters away.
Where are you at right now with UFOs? You in or you're out?
I'm still in on something, but I don't know what the object is or what it is.
But we've both been in and out.
The consciousness thing. I'm on that this week or month.
Oh, the one where they think they can call them in?
Not just that you need consciousness to use it or talk to it or see it.
Maybe.
I have no idea.
Maybe. There was some talk of gravity propulsion systems in the 1950s, I believe. There was some work that was being done, and there was some discussion about whether or not it'd be possible to use nuclear energy to create some sort of a gravity drive. What is your thoughts on that stuff?
Well, I think in order to do so, I'm gonna use a different parlance, right?
Instead of like obviously I don't know what I'm talking
about. No,
that's
okay, that's okay, right? So in terms of some of the language that we use in the literature when we talk about something that would, I think, trace to what you mean when you say a gravity drive, right? We might use the parlance space drive, right? And so conceptually, it would be a form of propulsion that instead of using some form of onboard propellant in a tank, right, it's found some way to couple to some external field, whatever it might be, and can generate some kind of a propulsive force. And so in my mind, in order for us to ever be able to go down a path where we're trying to create something like that might look like that or smell like that or what have you, we need to have a deeper understanding of gravity, right? And so, we just talked about E equals mc squared, and so I'm going to back up just a minute. If you think about everything we know today in physics as a Venn diagram, there are two circles on this Venn diagram, and they touch at a little tangent point. One of those circles is quantum mechanics that helps us understand how atoms behave, how light moves. And in the other circle, we have the words general relativity. And so that helps us understand how the cosmos evolves, how stars move and galaxies move. And so those two circles touch at a single tangent point. They don't overlap. So what that says is gravity, we don't know how to connect gravity to quantum mechanics. We don't understand that. But in terms of all of our daily life, just that level of physics helps us every single day, right? This cell phone is only possible because of quantum mechanics, and GPS is only as accurate as it is because we use general relativity to correct the atomic clocks on the GPS satellites. But until we develop a better understanding of how gravity might connect to quantum mechanics, or alternately how quantum mechanics might connect to gravity, I don't know that we'll be able to make meaningful progress, right? And so we need more circles on the Venn diagram. Just those two aren't enough. There are a number of people that would speculate that quantum mechanics is incomplete, general relativity is incomplete, perhaps it's even emergent. I think you had Hal Puthoff on here a few days ago, right? And he talked about a physicist by the name of Sakharov who talked about the fact that I think he was one of the guys that first pioneered the thought process. Maybe gravity is simply an emergent phenomena, and we'll develop a better understanding as we add more circles in and around the quantum mechanics circle, if you will. And so I think in order for us to be able to, come up with a widget, right? Some widget that generates a force in the form of a space drive, we're going to have more physics than what we currently have.
So we'll have to have more of an understanding of what gravity actually is.
Yes.
And what generates gravity.
Yeah. And it's not just the gravity thing. It's quantum mechanics. 'Cause quantum mechanics is completely incompatible with general relativity, right? And so this is a big issue, right? There are tons of people that spend their entire life trying to figure out how to unravel this mystery. It's a big conundrum.
Well, it's so fascinating to me because if you were a scientist in the 1400s and you were having this discussion with those people, they would think you're a wizard.
Absolutely, especially if you held up something like that.
Yeah,
man. Good grief, I'd get burned at a stake.
Imagine
right?
they show the screen,
right?
And
right.
I said, Jamie, pull something up.
Yeah,
like,
pull something up.
What is he doing? What is happening?
What is it that you showeth upon thy wall? Right.
So imagine. Extrapolate. Imagine going in the future and seeing what all this stuff is going to look like once we gain more and more understanding, which more scientists, more researchers piling on their discoveries, and then ultimately one day we'll be looking back on 2025 going, look at those barbarians.
Oh my gosh, did you see that show with Sonny and Joe where they were talking about what a bunch of maroons?
They didn't even know what gravity was yet.
My gosh, yeah.
It'd be like bloodletting. It's really kind of interesting because I bet every current civilization thinks it's at the pinnacle, and that everybody else is a moron, and we are a seriously advanced society.
Right.
AG1 has been a longtime partner of the show, and I'm excited to share some big news. The new AG1 NextGen formula is here. They did a bunch of research and improved their formula to make sure it's the best it can be. The same single scoop once a day, same subtly sweet flavors with those hints of vanilla and pineapple, but now with upgraded probiotics, vitamins, and minerals for even more comprehensive formula. AG1 NextGen is clinically backed with 4 human clinical trials, and it's shown to fill common nutrient gaps even in healthy eaters. Plus, AG1's NextGen travel packs now come in upgraded packaging. They're easier to tear, pour, shake, and go so your daily nutrition is even more seamless wherever life takes you. So subscribe today to try the next gen of AG1. If you use my link, you'll also get a free bottle of AG1 D3, K2, and AG1 welcome kit and 5 of the upgraded AG1 travel packs with your first subscription. So make sure you check out drinkag1.com/Joe Rogan to get started with AG1's Next Gen and notice the benefits for yourself. That's drinkag1.com/Joe Rogan.
It's interesting. You know, I get a chance to go do a bunch of discussions with students all over the globe, right, and talking about space exploration, specifically, you know, advanced power and propulsion. Right, I really kind of get into this whole difference between to space and through space. And so, as part of that narrative, right, I always spend a little bit of time telling them, right, we live in a society where everybody likes to pretend like we got all this stuff figured out, right? There's nothing left to figure out, right? You know, we got cell phones and internet and airplanes and all different kinds of stuff. There's really nothing left.
Just maintain what we have.
Right. Well, yeah, exactly. Yeah. And so I like to remind them, right, when I talk about, well, let's talk about that. What do we know? And then I kind of take them through that little thought process of the Venn diagram, just to say, hey, look, right, these two models are not compatible. That says there's a bigger circle, right, that connects the dots between all this stuff. And I highly doubt we'll ever come up with a single step that goes from just the two circles on the Venn diagram to a final one, some grand unified theory. I don't think we'll ever take like one single step. I think it's going to be a series of a bunch of different steps by a bunch of different people over many generations. And it's like there's so much stuff to go figure out. Come help us push back against the darkness. Help us, forever hunting the edge of the map, if you will, right? And so I think sometimes in today's society, we get lulled into this sense of security that we got it all figured out. Right? I mean, we got AI, it says all kinds of neat helps us out, all these different things. And so we get lulled into this sense that we've got it all figured out. And there's so much mystery out there for us to go figure out.
Also, there's a lot of people that are full of shit that are muddying up the water, so it's very difficult to know what is exactly true at any current moment.
Yeah.
I mean, just in the UAP world, there's a ton of grifters. There's a ton of people that are just putting sensational nonsense out to just get a bunch of clicks.
In some ways, when I talk to students and I kind of give them suggestions and advice and mentoring, it's like if you've got some particular area that you're interested in and it's highly technical, go do the work that's necessary to give yourself the math skills, the engineering skills, the science, whatever you need. Make sure you're equipped, right, so that you can, whatever's in front of you, you can go look at it with a discerning eye, right? Because like you said, the internet's changed the world for both the better and the worse, right? The signal-to-noise ratio has changed a lot. There's a lot of noise out there. And so the best thing you can do to try and cope with something like that is just to make sure you're trained, right? And you're capable of being able to discern something that's real versus something that's, nonsense.
So what is real in terms of, at least conceptually, what is real about warp drives?
The great question. When we talk about space exploration, right, a lot of times people think of like a Falcon 9 rocket, Saturn V, or a space shuttle, and these are all wonderful examples that should come to mind. But this is what we need to get to space, right? You got to climb against the gravitational well, if you will, and get into space. But when you get into space and you want to try and move through space, right? The things that you might use to solve that problem in an optimal sense might look very differently from the idea of rockets to get you to space. And so through space, there's a lot of things that we can bring to bear. But this gets into, I think, a larger framework I'd like to unpack with you today to talk about this through space type of thought process. But since you specifically asked about warp, I'm going to kind of jump forward.
Okay, sure.
I'm going to jump forward on the discussion thread.
We don't have to. We can use it as a teaser.
Okay, let's use that as a teaser.
Okay,
let's back up then.
Okay,
so I provided a a video that we pulled together called Go Incredibly Fast. I did it with a Swedish digital artist, Eric Ornquist. He's done a bunch of wonderful videos for NASA and a bunch of other friends. But this video kind of encapsulates the challenge of time and distance in space, right? If you want to send human beings past Mars and the solar system, that sets up a problem statement, right, that changes the nature of the types of technologies that you might think about bringing to bear to solve the problem. And so this video tells us what are some things that we can do to solve this problem, spanning from things that we kind of know to things that we kind of don't know in terms of both physics and engineering. And so this video is kind of an emotional encapsulation of a highly technical story. So let's watch. This would be a great way to kind of tee off this discussion.
The sky calls to us. We do not destroy ourselves. We will one day venture to the stars. Carl Sagan.
As incredible as it may seem, there will be a time, and it may be closer than you think, when we live on other worlds. The moon, Mars, and in the space between. And when that day comes, just as always, our children will look with curiosity across these new horizons, with a desire to go further and to explore what lies beyond. But beyond Mars, the distances between worlds grow immensely, even within our own solar system, and become truly vast in between stars. If we ever want to reach out across these distances, we need to learn how to go fast.
Nuclear electric propulsion. Here we go.
Yeah, so this is what we know. Using our current knowledge of physics and engineering, we could build nuclear locomotives to take humans to all the worlds in our solar system. But a starship powered with a nuclear heart aimed for even our closest star, Proxima Centauri, would have to harbor hundreds of generations of people, all living their entire lives aboard before reaching its destination 4.25 light years away. It would take 2 years just to reach the orbit of Saturn, and another 2,000 years to reach Proxima Centauri. We need to be able to go faster.
Fusion propulsion.
We should re-record this with you doing that for each of the vignettes.
Current knowledge of physics, but with engineering we have yet to develop. We can imagine a propulsion system with the sun for a heart, a fusion engine that could accelerate a starship up to 5% of the speed of light. This ship could cross the orbit of Saturn in 6 months and reach Proxima Centauri in just over a century. But if we want to traverse interstellar distances in less than a human lifetime, we have to go incredibly fast. The universe has shown us that this can be done by altering the scale of space itself. And we are working to develop new understandings of physics to learn how this might be controlled. If we could construct a starship with a propulsion system that decreases space in front of it and expands space behind it, this ship could cross enormous distances effectively faster than the speed of light. Such a ship would reach from Mars to Saturn in just a matter of minutes and be able to reach Proxima Centauri in less than 6 months.
Whoa.
From there are no limits to where we could go. Perhaps one day, humanity will look up at an alien night sky and strain to find the pale yellow dot that is our sun, our home, and know for the first time, as we look back on ourselves, that we are not alone in the universe. This journey starts today.
Whoa. First of all, whoever did the graphics
Thanks,
for
Jamie.
that.
Yeah, Eric Ornquist was the Swedish digital artist that we used to develop that video, and so
That guy nailed it.
oh my gosh, didn't
That's
he?
pretty
Yeah,
cool.
yeah. We had a 3 swim lane chart, if you will. That's a very technical version of this. We have a copy of it. We don't need to bring it up, Jamie. I can just do it verbally here. But it kind of encapsulates that thought process of this time distance problem. When we think about space exploration with humans, we think about Mars, right? We've sent human beings to the moon. We're probably going to go back to the moon sooner rather than later, and then eventually we'll want to send human beings to Mars. But what if we wanted to send human beings to Saturn, and we want to get them there in 200 days? That's a time frame that's kind of compatible with what we've thought about for humans to Mars, 180 to 220 days. If you frame the question that way, the amount of energy that's necessary to get humans to Saturn in 200 days is an order of magnitude more energy than it takes to get a payload from the surface of the Earth to low Earth orbit. So all that to say, right, that particular problem, chemical propulsion can't solve that problem. And so this is starting to kind of frame the discussion, this narrative that we've pulled together when we talk to students all around the globe, the difference between to space and the difference of through space. When you talk about through space, the distances are just so big, right? You have to rethink the problem, especially when you constrain it with how long does it take to get there, right? And so this particular video encapsulates things that we might do to solve problems like that, and maybe even into another star system, talking about things that we know. Like the very first part of the video, the vignette was, like you said, nuclear electric propulsion. I can't do your voice very well, right? Nuclear electric propulsion, right? And so this is a situation where it's known physics, known engineering. We've got a nuclear reactor that's fissioning uranium, let's say. It's splitting apart atoms, and that's the source of energy. You use that energy to plug into some form of electric propulsion. Like you got the neon sign that's behind you. Imagine you could take one of those tubes and cut the end off and allow the blue or green glowy bit to come out the back, right? And so the efficiency of electric propulsion versus chemical propulsion is much better. And so that's a way we can potentially think of a spacecraft architecture, nuclear electric propulsion, a nuclear reactor coupled to some form of electric propulsion that allows us to send human beings to Saturn in 200 days. And technically speaking, that capability, if we didn't invent anything else beyond that, that would allow us to send human beings everywhere in the solar system. That's why that's extremely important. And now we're getting into the passion of what I fought for so hard working at NASA to try and advocate for this understanding of the big difference between these two types of problems, if you will. If we make up our minds to perfect the idea of nuclear electric propulsion as a capability, I mean, that unlocks the whole solar system, right? And that's just kind of like the tip of the iceberg. And so the video then goes on after we kind of say, nuclear electric propulsion can open up a lot of stuff for us, but it's still going to take, you remember how long it said to go to Proxima Centauri? It was like,
100 years.
2,000 years for the new.
Oh, that's right.
So, I mean, I don't know about you, but that better be one comfortable window seat, right? That's a long time to be on a flight, if you will.
Now, how screwed up
Yeah,
are the
right.
people that live,
Right.
because you're inbreeding.
Yeah, well, it's good.
You know?
It's going to be generations, right? So either
it's going to
you,
be generations. You're going to have babies, and
Yeah.
like with who?
yeah,
Like,
right,
how are you going to do that? How are you going to choose? We're going to have arranged marriages in space. Is
Right.
that progress?
right.
You know,
Well, right,
Gonna
right.
force people to carry
Yeah,
children.
yeah, or they might be frozen. Like, what was it? What's that movie? with the blue aliens. I can't remember.
Right. Imagine if they're debating a woman's right to choose while they're in space.
Oh
Like,
my
you know what I'm
gosh.
saying?
Oh
Like,
my gosh, right.
It gets weird.
Yeah. So
We need to keep civilization.
Yeah,
Like,
right.
If you all commit, but I didn't commit, my grandparents did. But you're still on this thing forever.
It's like, my great grandparents committed, right?
This episode is brought to you by Visible. Now you know I tend to go down a lot of rabbit holes. I want to know everything about everything. And if you're like that, you need wireless that can keep up. Visible is wireless that lets you live in the know. It's the ultimate wireless hack. You get unlimited data and hotspot, so you're connected on the go. Plus, Visible is powered by Verizon's 5G network, meaning fast speeds and great coverage. And with the new Visible Plus Pro plan, you get premium wireless without the premium cost. And the best part, it's all digital, no stores. You can switch to Visible right from your phone. It only takes about 15 minutes, and then you manage your plan in the app. Ready for wireless that lets you live in the know? Make the switch at visible.com/Rogan. Plans start at $25 a month. For the best features, get the new Visible Plus Pro plan for $45 a month. Terms apply. See visible.com for plan features and network management details. Not only that, the reality is, by the time they get there, the human beings will have created technology that far exceeds that and probably beat them to it.
Yeah, you kind of see that hinted in the video too, right? Where you got the slow boat, and then you got the Fusion's the next one that comes by, and the guy's like waving as he goes by.
Well, for
to the other
sure,
one.
you would be a sucker to get on the first ship. Because by the time it gets there, the new ships will have already been there for months.
Yeah. They'll welcome you when you arrive, right?
The grandchildren of those people will welcome you.
Yeah. So the fusion propulsion is kind of the next step in the story. And so when we make that step, we're a little bit into the unknown, right? We understand the physics, right? The sun at the center of our solar system works on fusion. It fuses atoms together instead of splitting them apart to generate electricity. And so fusion propulsion is kind of another step in capability, right, that allows us to do maybe do an interstellar mission that's measured in 100, maybe 200 years. Still kind of long, but that's a lot more respectable than 2,000 years. But contrary to what the movie Iron Man might say, we don't have fusion reactors that are gigawatts the size of this coffee cup, right?
You stick in your chest.
Yeah. We got a little work to do before we get there.
Well, that comic book was written probably in the 50s.
Right.
So when you think about this kind of progress, this ability to generate that amount of power and to bend gravity and to bend space, what kind of a timeline do you think we're on for something like that?
That's actually one of the most popular questions I get when I go talk to students, right? Whenever you talk about that last swim lane in the video, the idea of a space warp, you can expand and contract space, and that allows us to potentially go somewhere in months, whereas we were just previously talking about millennia and centuries, right? And so just to remind folks, we just talked about everything that we know of physics today, quantum mechanics, general relativity, right? We got to add some more stuff to the Venn diagram to develop an understanding. And so my crystal ball is no better than yours, Joe. I couldn't say specifically if, when something like that might happen, but I can say I actually do know what we need to be working on right now. Right. And so in that context, right, I'm certainly doing the things that I think might help make meaningful progress towards that type of operative goal at some point in time. But, I just don't know how long it might take. And so let me kind of give an experience that I had. I taught at International Space University over in Strasbourg in France. And they have a cathedral there in Strasbourg, absolutely stunning. But the thing that's even more interesting about this structure, it's like 500 feet tall. They started building it in 1100 AD, and they didn't finish the cathedral until 1700 AD. So the people that built the basement had no hope of seeing the finished product. All they could do was imagine in their mind's eye what it might look like. But they knew what they needed to do to kind of make meaningful progress. And so they did their work, and then they hand the baton off to the next generation. Maybe they're putting the floor in, and then another generation does the buttresses and so forth. So from that standpoint, I think sometimes it's important to, we talk about teamwork, right? Teamwork is a great thing. But teamwork, we typically think of shoulder to shoulder, right? But I think there's also value in teamwork across generations, if you will, right? In a day and an age where you get impatient if you text somebody and they don't text you back in like 30 seconds,
right.
I think we've lost an appreciation for the value of what that means, right? In terms of working over stuff longer than what your horizon might be. I'd love to see the idea of a space warp, before I go to the next chapter. But I don't know that will happen for sure. But I do know specifically what I need to be doing. And so from that standpoint, that's how I grapple with that particular question, because it's a wonderful question, and I would love to be able to tell you a very concise answer that would fit with what I would hope it would be, but I don't know for certain. But I do know what I need to be doing next, and that gets into, maybe we can unpack that in just a little bit. That gets into the idea of how the idea of a space warp works and how that traces back to those two circles on the Venn diagram,
Well,
quantum mechanics and general relativity.
Let's talk about that.
Yeah, so maybe what we can do, Jamie, I sent you, there's a slide that's got like a cartoon space warp with looks like a little sheet of a mesh or something like that. I don't know how to explain it. If you could pull up.
There it is.
Yes,
oh, wow. How
yes,
cool does that look?
That's the one. So we actually did that graphic on the right for Nature, the journal Nature. They were doing an article on the 50th anniversary of Star Trek, and so they asked us to pull together that graphic.
Oh, cool.
And so this is an illustration of the idea of a space warp. Let me give just a little bit of background. In physics, there is a speed limit that we have to acknowledge when we talk about trying to go somewhere really quickly. Right. And so I like to call it the 11th commandment of physics, thou shalt not exceed the speed of light. Right. It's kind of a hard and fast speed limit. And so if you talk about trying to get to another star that's 4.25 light years away, that should automatically set in your mind, well, shoot, we can't get there any quicker than 4.25 light years. Right. Well, there is a little bit of hope because there's a loophole in general relativity that establishes that hard speed limit. General relativity says we can expand and contract space at any speed, and we see evidence for this when we look at the nature of the cosmos, right after the Big Bang, 14 billion years ago, there was something called an inflationary phase, right, where if you were to pick two random points in this expanding bubble of the early cosmos, you stood on one point and you looked at another point and figured out how fast it was moving away from you. It would move away from you like 10 to the 30th, 10 with 30 zeros times the speed of light. So, yeah, we're really, really, really fast, right? And so we know from astrophysics and cosmology that this is possible. And so this idea was kind of rattling around in a physicist's brain called Alcubierre, who said, hey, well, this is interesting. Nature can do it on a grand scale. Can we potentially do it in a purposeful way? And so he published a paper in 1994 that kind of encapsulated the mathematics for this idea. And if you take his mathematics and you put it into physical form, it's going to look like my little cartoon here on the right. And so you got the little ring that goes around the little surface here. It looks like a wave. And then there's a little central portion there. It kind of looks like a football, let's say. And so what happens is that ring that goes around that little football, that's what's necessary to make the trick work. And so it has to be filled with something called exotic matter. And so that's an important issue, right? What's exotic matter, right? So it's something in general relativity that's also equivalent to negative mass. And so we all understand positive mass, right? If your little brother hits you on the head with something, that's positive mass hitting your head, right? Negative mass is not only zero mass, but it's a negative value. And so what does that even mean? And so in the context of general relativity, if we come up with a model that requires exotic matter, we have to highlight that as a problem because we don't, in general relativity doesn't tell us how to make that. And so that could potentially be an obstacle that would prevent something like this from ever being physically real. But if we could figure out how to make it, and I'll actually speak to that in just a second, if we could make that and we could create a ring that could manifest that exotic matter, it would cause space-time to respond in such a way so that it would expand and contract to allow you to go to Proxima Centauri in 5.5 months, as measured by you on board the spacecraft in that football, and as measured by folks over in Mission Control over in Houston.
Now, this exotic matter, what do you speculate that would, what would that be?
So exotic matter, and this the cool thing is, these are the equations. So there'll be a test later, Joe. So you know.
Oh, I'm ready.
So in Alcubierre's paper in 1994, right, he rightly highlights the fact that, hey, there's a problem. Danger, Will Robinson. This stuff requires exotic matter. That may mean it's non-physical. However, he highlights the fact, hey, we have this other circle over here called quantum mechanics. And there's something in the context of quantum mechanics called negative vacuum energy density. And so that's something that's connected to the idea of the Casimir force. We'll unpack that later. But that is something that could serve as a proxy for the idea of exotic matter and may help us one day make the idea of a space warp a physical, real thing.
Whoa. So this ability to go as fast as you're describing, where you could conceivably make it to other solar systems.
Yeah.
This obviously is a version of it that will probably be improved upon.
Mm-hmm. Right.
So if this ever does come to fruition, you could conceivably imagine a time where you generate even more power, have even more capability, and you can go everywhere in the universe.
Right. Potentially. Yeah, it unlocks just about anything. Let's go back a slide real quick, Jamie. I want to share something with you. So the next time you're in an airport, you can do this, right?
Okay.
So if you want to try and imagine the idea how a space warp works in theory, if you will. This is just a thought experiment. So thought experiments aren't exactly precise, but they do help communicate the idea. So when you go to an airport and they've got those long conveyor belts, if you will.
Yes.
I think they call them travelators. And so they help us move quicker between gates.
Yeah, by the way, folks, you're supposed to walk on those things.
Yeah, right, exactly.
You hear me?
Absolutely.
Walk.
Right,
lazy
right.
fucks.
So if you think about what happens when you make use of one of these travelators, it's just like you said, most of us walk, right? So when we're at airport, we're walking, we're dragging our bag, and we usually walk about 3 miles an hour. And then when we get onto the belt, we keep walking. Now, if you think about so let's say Jamie's sitting at a gate and he's watching you walk by. Before you get onto the belt, he sees you walking at 3 miles an hour. When you get onto the belt, all of a sudden to Jamie, it looks like you're going 6 miles an hour. So what's going on here? Well, think about the belt, right? The length of the belt in front of you. What's happening to it? It's technically it's going underneath, right? 'Cause this is a metaphor.
Right.
It's going underneath, but the length of belt in front of you is actually contracting. Right. And so by the same token, the length of belt behind you, yes, it's a conveyor belt, but it's expanding behind you. So the belt is contracting and expanding in such a way that it now seems like to Jamie that you're moving at 6 miles an hour. So the next time you go to an airport and you get onto one of these travelators, I want you to put your hand on the railing and say, engage.
Well, that's a great comparison. Totally makes sense if you think about expanding that idea just infinitely with gravity and just being able to...
Right. And
that video, by the way, is so cool. Like the way he generated that and looks exactly like these people describe things they're seeing in terms of, when people find UAPs that are particularly unusual.
Right. Now, the cool thing is if you pop forward one more slide, Jamie. There we go. When you look at the math and physics associated with this, right, the proper acceleration alpha on board the spacecraft is formally 0. So what that means when they turn the warp on and off It doesn't like splatter the crew against the bulkhead. You talked about, in the beginning of the show, we talked about G-forces. Right. And so I don't know if Alcubierre specifically was hoping to land on that kind of observation, but the little toy model that he came up with has got a lot of appealing characteristics, and that's one of them, right? When you turn the warp on and off, the proper acceleration alpha is formally 0, so it's actually 0G. So
That's
he stumbled into a really nice solution, if you will. If you don't mind, while we're here, I'd love to maybe spend just a second to talk about life imitating art. There's some interesting things that I think it's the next slide or two. Keep going. We'll come back to this one another time. So this is it's a modern rendering done by Mark Rademacher, a digital artist from the Netherlands I've worked with over the years. This is a Star Trek ship concept that was developed by Matthew Jeffries in the 60s for the TV show Star Trek. And so you might notice there are some qualitative similarities here to this little structure, to the little gray cartoon that I just showed you. It's got the rings on it, right? It's got this little central structure. But there are actually a couple of fatal flaws with this concept. But the thing that's fascinating to me before we talk about the things we're going to fix is Matthew Jeffries is not a physicist, number one. Number two, the math and physics associated with the idea of a space warp hadn't been published in the 60s when he came up with this artwork. But look how close he got. Right, for somebody just following his gut instinct in terms of pulling something together.
What was his background? Did he have some sort of a background in science?
I couldn't say. I don't know for certain, but man, he sure did.
He nailed it.
He sure did get close.
He got so close. I would almost,
yeah. So the interesting thing is the nature of this ship, the fatal flaws that it has. So we did an update of this as part of like an education outreach. So I reached out to Mark Rademacher and some folks from CBS Studios, and so we did an updated version of this for a Star Trek Ships of the Line calendar.
That's cooler looking.
Yeah, and that's the one that's in the video, right? The IXS Enterprise. Go back just one slide, Jamie. So the problem with this version here is the rings that go around the spaceship are entirely too thin. So when you calculate how much of the exotic matter I just talked about that you might need to make this thing do something useful, it's going to be a very large number that might be impossible to ever make. So that's like fatal flaw number one. Fatal flaw number two is the bridge of the spaceship goes way out in front of where the warp bubble would form as a result of those rings. So the rings would form like a warp bubble that looks like a little capsule. It would actually cut the bridge off, and the bridge would go floating away, and Scotty would be so fired. Right?
That's not good.
That'd be a short, sad episode of Star Trek.
Yeah,
so
I hope they have a parachute.
Right, exactly. So we work with CBS Studios. Now you can go to the next slide. So now we've got, the rings are much more athletic. They have more heft to them. They're thicker, so that reduces the energy requirements. And then the spaceship itself is kind of properly nestled into the warp bubble.
It just looks cooler.
Right. Yeah.
Like all things from the past, they can make a better version today.
Right.
So this exotic material, do you imagine that this is an undiscovered element? Do you what's the theory?
Right. And this is the reason for some of the lamentation, right, about general relativity and quantum mechanics. General relativity just doesn't tell us how to address it, right? It just simply says you have to highlight it in your paper before you submit it for peer review and say this may cause problems. But quantum mechanics has this stuff called negative vacuum energy density, right? And so maybe we can unpack that.
Please do.
So what is negative vacuum energy density? So let's talk about some of the implications of quantum mechanics and how they're a little different from our day-to-day experience at the macroscopic level, right? Empty space in quantum mechanics is actually not empty. So if I told you to think about a vacuum chamber, right, and I told you the vacuum chamber is under vacuum and there's nothing in the vacuum chamber, right? And that operative word, nothing, right? That you have vacuum pumps that turn on and pull all the air out, so there's nothing in the vacuum chamber. Quantum mechanics says, wait a minute, hold on. The idea of empty space, even though there's this classical vacuum, right, that we might think about. It's not actually empty. There's these fluctuating fields and forces that are always going on all the time. So even though like this is Plumbrook, NASA's large vacuum chamber up in Ohio, and so if you imagine you took that vacuum chamber and pumped on it so there was no air on there, and then you might say there's nothing in that vacuum chamber. Well, quantum mechanics says that at the microscopic level, there are fluctuating fields and particles all the time. And so this sounds very, 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 counterintuitive to what we experience in our day-to-day life, right? You pick up a coffee cup and you push against a door, right? That's how we think of the world, if you will. But quantum mechanics deals with the microscopic realm, and things are a little bit different. And so that's kind of background. So you can this peculiar nature that I'm explaining to you, you can actually do an experiment that provides you a observational consequence of this peculiar nature, and it's called the Casimir force. I think I have a slide in there, Jamie. So the Casimir force can be thought of in the following way. Imagine that you've got two metal plates, like you see here in the graphic. You put them very, very close to one another. That separation distance is maybe 100 nanometers, so certainly much smaller than a human hair. Very, very small distance. And then you imagine you have a vacuum chamber that you put these two small plates in, and then you turn on the vacuum pumps and you pull all of the air out. So there's nothing in there, right? At least that's the way we would think about it. So now we're going to conduct a little thought experiment. We're going to imagine that Jamie has superhero powers, and he can shrink himself down to being a wee tiny little atomic person. And we're going to ask him to go into the vacuum chamber, and we're going to ask him to measure the pressure on the outside of the plates, and we're going to ask him to measure the pressure in between the two plates. And so we're going to expect, based on the normal way we exist, he's going to say 0, 0 on the outside, and he's going to say 0 in between the two plates. But what he's going to report back is he's going to say 0 pressure on the outside, like we expect, but he's going to say there is a negative pressure between the two plates. Well, what the hell is going on? Well, the quantum field is full of fluctuating fields and forces. Matter is both a particle and a wave. You may have heard that statement at some point in your life. And so all these little bits of energy, right, they have wavelengths associated with them. And so any wavelength that is bigger than the physical gap of the cavity, it won't be able to manifest between the cavities. So when we add up all the bits of energy on the outside, that's our 0 reference. When we add up all the bits of energy on the outside, and then we add up all the bits of energy in between the two plates, there are less bits of energy because all the bigger wavelengths are excluded. And so there is a deficiency of vacuum energy that manifests between the two plates, and that results in that negative pressure that wants to pull those two plates together. That's called the Casimir force. A guy by the name of Casimir was a guy that derived that back in 1948, but it took us until the late 90s to actually measure this in the lab to the physics community's satisfaction. And so it's been studied hundreds of times since, measuring forces at different regimes, if you will. And there's also something called the transverse Casimir force. So when you try and slide those two plates relative to one another, the vacuum wants to resist you sliding those two plates. And so this is a very real phenomena, and it's a wonderful illustration of the peculiar nature of reality at the microscopic level, right? So, the theory was worked out in the late 40s. The experimental stuff was started in the 90s, and then there's been a bunch of work since then. And I think they're even looking at trying to use the Casimir force in MEMS devices. But all that to
what is a MEMS device?
Micro electromechanical machines, some small gears that you can't see with your eyes, but they serve different purposes that people are trying to come up with for sensors, maybe some things in your car, some future chips that might be in your phone or something like that. Things that where they make micromechanical systems that they make them with light because you can't even see those kinds of things. So the quantum vacuum, this fluctuating field of particles and forces and so forth, is a very real phenomena. And so this stuff I just described to you is the negative vacuum energy density that Alcubierre highlighted in his paper when he said, we don't know how to make exotic matter in general relativity, so that circle on the Venn diagram doesn't tell us where to go. But quantum mechanics tells us how to make negative vacuum energy density in the context of what we see in a Casimir cavity. And so maybe we can, some future generation of scientists will figure out how to do something in some way to, like if you ask what's in those rings around the IXS Enterprise, right? Maybe it's some deeper understanding of the nature of the quantum vacuum. And point in fact, I talked to you about, you asked me when might this happen? And I said, I can't tell you when, but I know what I need to be doing next, right? And so in my mind, I think some of the next big chapters in physics are going to be centered around understanding the nature of the quantum vacuum and the quantum field. I think there's going to be a lot of fruit there, and that may provide us the opportunity to add more circles to the Venn diagram or maybe expand one or what have you and so forth.
So what kind of experiments have to be conducted in order to expand this? Like, are you talking about things that are going to be achieved in particle colliders? Like, how are they? Like, what do you anticipate?
That's a good question, and I'm there. So there's a lot of different approaches people have taken to try and explore the nature of the quantum vacuum, and you could even start to look at cosmological observations. When we talk about dark energy, right? That's equated to the quantum vacuum at scale and the cosmological scale, if you will. And I think there's even some recent stuff that's come out in the peer-reviewed literature that the cosmological constant may not be constant. It may actually be changing over time. And so there's some experimentation. It has nothing to do with the idea of a space warp. The people that do work on that could care less about space warps, but they're trying to understand the nature of the cosmological constant of the quantum vacuum at scale. So there's a domain where some interesting work might be done. I know universities all over the globe still do work today with studying the Casimir force. They make different types of things, different materials and so forth, just to try and understand how materials respond when they make these small things and trying to understand how the quantum vacuum works with it. But I think there's also some other things that we can try, right? And so that goes, I think you've seen some of our work that we've been doing, right, with some nanostructured devices that we've been doing some work for DARPA for a number of years, where we're actually trying to work on some systems that generate power. And so in the process of doing that, we've actually found that our nanotechnology may actually have some intersections with the idea of a space warp. So I think it's
when you're saying that, like, our nanotechnology might be used to create some sort of a space warp. Like, in what way?
Right. Jamie, can you pull up one of those slides close to the not that one. Go back. Keep going back a little bit more. Keep going up. Go right there. Right there. So there's this on the left-hand side of this image. There is a scanning electron microscope image of a nanostructure that in this case, we 3D printed, and then we metallized it. And so the work that we were doing for DARPA associated with that structure is focused on trying to harvest energy from the quantum field. And so we've been working towards trying to generate a voltage potential on that little structure where the pillars in the middle are at a different voltage from the walls that are in the picture there. And in the process of doing the analysis to help us understand how thin do we need to make those rod-like structures you see inside the cavity gap, when we study how the quantum field responds to those structures, we noticed a kind of an unanticipated intersection with the idea of a space warp. If you look at, there's like in the picture, there's like a little blue surface overlaid on top of the center pillar there, and you've got those two little regions that are like yellow. I think Jamie just moved his mouse over those, right? So that's the pillar, and if you move up, that blue surface shows the quantum field's response. So that negative vacuum energy density distribution you hear me talking about, that is like a section cut in terms of what that looks like. And so we're trying to make sure that the nature of that distribution allows us to see a voltage difference, right? Which we do see, but that now we can go to the middle pane here. The top picture there is that image on the bottom left, and so you see those little yellow, kind of looks like a lenticular shape. And then if you look at the picture beneath that, that is a section cut of a space warp, that ring that goes around the spaceship. So if you look at the distribution of the exotic matter on the bottom pane versus the distribution of negative vacuum energy density in the top, they're qualitatively very similar to one another. So we, as part of an extra credit, right, we're still, DARPA doesn't care about the idea of a space warp, to be clear. They don't care about that. But this, as scientists, we were interested in, wow, we didn't expect to see this. This is interesting. And so we took that insight and we said, all right, the distribution that's on the left around that center pillar, it's prismatic, right? It's a straight up and down kind of distribution. It's not a ring, which is what we might think about when we think about a space warp. So we said, all right, well, let's do a slightly different model. Let's make a sphere inside a cylinder, and then let's study how the quantum field responds to that structure. And so the energy density distribution to that, the little green items there in the cartoon, the energy density distribution for that properly matches the requirements for the idea of a space warp. And so we published a paper. Yeah, this is significant,
Wow.
right? Because before we did that, the only thing we could talk about in the literature was just the math, right? If somebody said, well, what might you build to make something like that? All we could do is just shrug our shoulders and go, oh, right? And so this allowed us to go through and say, hey, now we can propose a real structure, right, that we can potentially, and you can 3D print that. There are 3D printers that print down to that level, right? We could 3D print those structures. Maybe some clever scientist will come up with a good experiment on how to go through and maybe study the optical properties of this. And somebody could do something like that where they could take our insights that we published in our paper, and then they could go 3D print some stuff and do some experiments to show that they can, hey, we've measured the change in optical properties associated with these little tiny warp bubbles that we're making on a chip, if you will. And so maybe that could be something a future scientist could do. But this is the first time in the literature that we can actually say, as a community, this is a real thing that we could go make, and it's predicted to manifest a real warp bubble. It's not going to go anywhere. It's not going to do anything. But still, that's significant as a measure of a paradigm shift in our understanding. So.
It's Leonardo da Vinci's drawing of.
That's a wonderful metaphor.
Yeah.
It definitely could be something like that, right?
Yeah, when da Vinci was drawing flying things. Yeah. Well, it looks like what you would expect something to look like in Star Trek that generated a warp drive, right?
Yeah,
doesn't
right.
it? Like you could see it lighting up.
Yeah, it has some kind of a humming noise, right?
Yes.
Sounds like a heartbeat or something, right? So
the idea of using quantum energy is so fascinating because I don't understand what that means. I don't understand the whole idea of subatomic particles because it seems so fake, seems so crazy that the universe is made out of things that are essentially working on magic. They appear and disappear.
Right.
They're in two places at the same time. They're both still and moving.
Right.
They're in superposition.
Right.
They're entangled.
Right. In the grand scheme of things, I would speculate that as we add circles to the physics Venn diagram, we may actually be able to change some of that narrative, right? So maybe some, and so this gets into, now we're getting into like the philosophical history of physics and some of the debates that have gone on for the better part of a century. But maybe as we continue to move forward and we add more circles to the physics Venn diagram, it'll instead of having this narrative or this framework where we talk about probabilities and chances and entanglement and the cat is alive and the cat is dead, right? Maybe there is a deeper level of understanding that we have yet to uncover, right, beyond what we know in quantum mechanics today. That helps us understand things at a more fundamental level. There is a sub-quantum dynamics, right, that explains the the randomness, the stochasticity that we see, and there'll be a much more satisfactory explanation for things where it's not like this. I would almost play back some of what you just said. If you think about it, it actually has kind of a bit of a metaphysical kind of sound to it, if you will, right? The collapse of the wave function. Well, what does that really even mean, right? So maybe as we continue to move forward and we get deeper understandings, we'll have answers that are much more compelling and logical in some way we don't currently understand yet.
Well,
right?
when you try to explain to people the double slit experiment, try to explain that to people, the waves and particles, like, what are you even saying?
Yeah.
Like,
you have one slit, you get a nice Gaussian distribution around a center point, then you open up two slits and you've got this weird interference pattern, right? It's like, and that's the whole matter is both a particle and a wave, right? That's how you kind of see that, if you will. But how do you explain that? And so actually there are, thought processes that people have to explain that type of stuff in some of the stuff that's out in the literature today. Bohmian trajectories is specifically one of the things, but
it's almost frustrating because I know we're going to crack it one day. It's like, damn, I wish I was born in 2090. You know what I mean? Like, they probably would have already nailed. Not really. I really like being born right here.
Yeah. Cool.
I love being alive right now because it's such a fun time where these technological innovations they're compounding and they're building on each other in such a very incredible way that this kind of experiment is actually possible, and now you can actually prove, we have a theoretical warp bubble. We can show you how we can make it.
Right. And so some of the stuff that we're focused on, right? So, I spent 20 years at NASA, and then I left NASA at the end of 2019 to go help stand up a nonprofit Limitless Space Institute where we did some of the work that we just showed you, right? And that's where we were doing some of the initial work for DARPA on the little nanostructures that we're working on. And so we got a lot further with that work than we thought we were going to, and so created a commercial company called Casimir, where we're trying to commercialize our power-generating nanotechnology. And so in some ways, it's like the interesting aspect of this story is in the process of us trying to pursue this romantic vision of the idea of a space warp, we may have stumbled into this power-generating nanotechnology that could be useful here and now in a lot of ways, right? Ranging from, powering the Fitbit on your wrist or tire pressure monitor system in your car. Maybe one day as we continue to grow the capability, it'll do a lot more than that. But, in the process of chasing the romantic dream, we've stumbled across some technology that might be useful in the here and now, right? And so when you ask what might be in the rings around that spaceship, the IXS Enterprise, maybe those could be long-standing descendants from some of the stuff we're working on in the chips that we're making in the lab today. Right?
Essentially, like the people who put the foundation for the St. Peter's Basilica down, they're not going to see the completed project.
Right, absolutely.
Yeah, and this is just how it goes with everything that's really extraordinary like that.
Right. It's neat to think. It's neat to think the speed at which innovation occurs. Right. I think you've had Elon Musk on this show a few times, and it's neat to see what he's been able to accomplish with SpaceX. I met him in 2003. This was the very beginning of his journey. Right. I was on a planning committee for a conference, American Astronautical Society, and we were doing a conference in Houston with a focus on a commercial space flight. So this is at the dawn of the idea. At the time, I was working at Lockheed Martin. And so we had Elon Musk come in and talk to us about this crazy idea of SpaceX that he had, right? And so Lockheed Martin corporate contacted me and asked me, hey, we know you're going to be interfacing with this guy. And so we want you to write up a profile on him after the conference and tell us what you think. And so I went to the conference and got a chance to watch a number of people come in, talk about great ideas, and Elon came and gave his talk and so forth. And after the conference was over, I wrote up a profile and submitted it to Lockheed Corporate. And I said, I think this guy is going to do everything he said he's going to do. I think Lockheed Martin should consider buying his company at some point in time. And so fortunately they didn't, right? Because I think if they did, they would have ruined the magic, if you will, right? So.
Yeah, you need it in his control. He's got some pretty bizarre ideas that, just watching them catch that rocket, you're like, what?
That's nuts. That is
So
absolutely nuts, right? My
So
brain
nuts.
looks at that and goes, no.
Right. It looks like, I mean, that's why the kooks on the internet think it's fake, because it almost looks fake. Like, how? It's such a leap above anything that's ever been done before.
Yeah. Yeah. Could you imagine the design meeting?
Right.
And I'm sure it was probably Elon that said this. Yeah, I want to catch a 20-story building.
Yeah.
I can see all the engineers. Is he serious?
Right. Exactly. Because everybody thought they just had to deteriorate and fall to Earth.
Yeah.
You know,
Right.
They run out of
Right.
gas.
Right.
You know,
Right.
when you're shooting the rocket up in the sky, and then you plan it so they fall into the ocean. Like, okay.
Yeah. I do think that. I don't know if you've ever met Gwen Shotwell. I think Gwen Shotwell is kind of like his secret weapon, right? So, Elon Musk strikes me as one of those guys that's like an idea generator. All this great stuff's coming out at the speed of light, if you will, and he's coming up with all these different ideas. But you got to have somebody who can take all that chaos and pull out the important tidbits and then put them into action, if you will. And so, I think Gwen is kind of his secret weapon. She helps take all of that chaos and then starts to put it into, actionable steps, if you will, to help SpaceX make
If that's the case, she rules.
Yeah.
Just imagine as technology increases, if you have someone with that sort of an innovative mind and someone like Gwen who can put it together as all these new ideas come to fruition, you could imagine where we're going to be with this stuff.
Mm-hmm. Right. Absolutely.
Well,
Yeah. And just to kind of put that in context, right? In my mind, SpaceX is an example of mastering the art of getting to space, right? SpaceX is conquering that climbing against the gravity well, as opposed to moving through space. Therein lies a great opportunity to kind of re-highlight that perennial difference, the challenge between the two, right? So
Right, moving through space.
Yeah.
And then the idea of some sort of a space station somewhere, like not just circling the Earth, but out in the cosmos. There's so many different ways they can take this stuff, and the idea of eventually colonizing other planets, which was always like people go, okay, well that's what we're probably going to try to do. Wouldn't another civilization do that to us? And that's where you get into the weird talk.
Yeah, right.
Whether or not
right.
it's actually happening.
Right. Well,
before.
I guess it gets into the whole, if somebody has the ability to come here, right, it's almost like I would rather be the one that was technically advanced and able to go somewhere else rather than have them come here, because that's
way better.
if you look at history, that hasn't ever gone well for the
Not one
for
time.
the organization, for the tribes that get visited. It just never tends to go well for them. So that's where I'm like, I'd rather be the one doing the visiting than
Exactly.
right. So.
And then imagine the exotic viruses.
Oh yeah, right. Oh, that's a good point.
it's another
It
problem.
always makes you think. Star Trek, they just they beam down to the planet.
No
so
problems. They
They
have air there.
Yeah, right. It's just like
They breathe air, same atmosphere, same
right.
pressure,
Yeah,
same
yeah.
gravity.
Right. It's like I keep waiting for the episode where somebody starts bleeding from their eyes. Right.
Right. Explodes the moment they land
the
on the
guy with the red
surface.
shirt. Right away.
Yeah.
Right. That guy's gone. Right?
Yeah,
So,
I mean, you have to take a chance.
Right.
But, when you think of what's currently available today in terms of research that people have done on propulsion systems, when people speculate that there's some sort of a black ops program that the government's been running secretly, and this is what a lot of these drones are that people are seeing, and this is what a lot of like the Tic Tac stuff, that it's probably our stuff, which is why it's off military bases. Given your understanding of the current state of science, do you think that's even possible?
Yeah, no. It's hard to imagine that being possible, right? Just in terms of because my entire professional experience has been about wrestling with, how do we conquer this time distance problem? And so I know all too well all the shortcomings. I know where we are for the most part today, where we're lacking, right? And so I don't know that there is an organization that has things that could potentially operate in the ways that like the Tic Tacs.
Right.
I don't know that there is a black ops that actually has that capability.
What
Right?
I'm kind of asking, though, is it even conceivable that there could be a program where you could get the brightest minds who are working on this stuff to make advancements that are far beyond anything that conventional wisdom describes?
Yeah, now I'm with you. I was on a different frequency. Thank you. If we had some kind of kit, right, that is not from here, however we got it, right, and people spent some time studying it, maybe they could figure it out. But that also gets into a little bit of a logic conundrum, right? Because I think you talked about going back to the 1400s and holding up an iPhone, right? If you handed something like this to Isaac Newton,
Right.
he would have no idea what to make of this, right? So he might figure out the interface, right? The Apple's done a good job of making this thing pretty user friendly, but I mean, how could he even if he looked at it with like a glass that allowed him to see, maybe start to make out the pixels,
Right.
He doesn't have the benefit of any of the math and physics and so forth. So it's possible, right? But those are the things in gaming situations in my head. What might that look like? Well, it's like, wow, this might be really hard to figure that out. But it'd be awesome if somebody had figured that out, if that was in the realm of possibility, right?
Speaking for the people that believe that they have recovered these vehicles from somewhere else, one of the ways they describe them that's really kind of bizarre is they describe them as donations.
I've heard that word.
If you were going to try to get someone to figure out how to construct their own automobile, you wouldn't give them a 2025 Corvette ZR1. What you would give them is a Model T. You'd give them some simple combustion engine, a carburetor that you could go, okay, like someone who knows how to make a locomotive, they could look at that and go, okay, I see what they're doing. Oh, wow. All right, so this thing, the combustion, and then the gases spin around, and then it creates energy, and then it spins these wheels. Then this thing has different gears, and that goes to the back wheels. Okay, I think we could do this. But, if you gave them some electric Tesla, like a new Model S Plaid, they would go, what the fuck is this?
Porsche 911.
Yeah, exactly. They would go, what is this? Well, especially electric.
Right.
Electric vehicles, they go, this is bananas. Like this thing goes 0 to 60 in 1.9 seconds.
Yeah, that's
it's
amazing.
a fucking car.
That's amazing, isn't it?
It does feel, if you've ever been in an electric Tesla, like the Model S Plaid, it feels like a spaceship. Like it feels like you're not in this time period.
Right.
You're in something in the future. So if they gave us something to back engineer, they would most likely give us a Model T.
Yeah. Actually, I had never thought about it that way.
Yeah.
Right.
You wouldn't just start with the best shit we have.
Right.
You know what I mean? Like, give these dummies a Jeep from the 50s.
Right.
You know what I mean?
Right. A Willys, right?
Carburetor.
Yeah.
Figure it out.
Yeah.
Look at all the stuff. You can work on it. Like if you open up the hood of one of those things, an old Jeep, you go, oh, I see where everything is. Here's the spark plugs.
Right.
Here's the distributor cap. I get it.
Yeah. Well, I guess, if that were the case, and I guess you could, I could follow you down that thought process, if you will. Right?
So then could you imagine, I'm just asking you because I know you understand science and you understand engineering. Is it possible that there could have been some program that's been going on in complete total secrecy, shielded from Congress, shielded from the higher levels of government, on the most need-to-know basis possible with our current security systems, that they could have some kind of a program that's working on this stuff?
I certainly couldn't rule that out, right? But some things I think about when I think about that problem. Let's talk about the F-117 stealth fighter, right? There was a program that was unclassified. I think it was in the late 70s, maybe the early 80s, called Have Blue. And so that's when they were first starting to explore the idea of having an aircraft that could be extremely stealthy. And so it was unclassified for a good amount of time until they put the first test shape onto a radar stand out in California in the desert, whatever the case may be. And then they turned on the radars and they're like, well, something's wrong because we're not seeing anything, right? And then a bird landed on the prototype and they saw the bird. And so when that happened, the whole program went black, right? It became classified. Before then it was not classified, then it was classified. But it of course came out in the 90s with Gulf War I, right? I think we saw some manifestations of this. And so there is a program that's extremely classified for the obvious reasons, but it still came out, right? And then I also think about, I worked at NASA, right? And so you have worked at NASA for 20 years, and you get the full spectrum of people serving different roles in a facility. And so you're always going to have people that, take out the garbage and do other different things like that. And so, if you've got something that has implications like that, I mean, it's hard. It could happen, but that's the thing I struggle with is that's, there's a lot of different moving parts to try and keep that big of a secret. I mean, maybe it could happen, right? So,
well, if I was running things and that was going on, I would talk to you. And it's like, look at this guy. And he seems to be on this pathway that we are currently exploring. I'd want to bring somebody in. And
well, if somebody's got a manual, right, that can help me figure out to go do something, give me a call, right? I'd love that. And I know I'm going to get all kinds of emails as a result of saying that, right? So
kooks.
I already get that now, right?
You're going to get the kooks. But, the question I guess I'm asking is, are there even experts in physics and engineering that are out there that could be quarantined, that could be taken away from everyone else and put on these projects? And could they achieve meaningful results given that kind of compartmentalized science?
Right. Maybe the thing that we could throw into the sandbox on this discussion is the Manhattan Project. Maybe there's a better example of something where they were working on something that was extremely important for humanity, and they were able to keep a lot of those secrets for quite some time. So yeah, maybe that's how you would have to run something like that, I guess. I don't know.
But would you have the expertise? Are we aware of who all of the experts are? Is it possible that the government could have had access to brilliant minds that are on this sort of path like you are, gotten them, moved them into these projects, and kept it all hush-hush? Is that even...
Certainly, the government also has an organization called the Jasons, right, where they have a lot of extremely smart folks from academia, and they come in. Typically, I think it's like a summer assignment, if you will, and so they band together in the summer to go work on a series of problems that folks might have, and so they kind of what you're asking me kind of makes me think about that kind of a mechanism where you have access to the best and the brightest across the entire spectrum of U.S. academia, and you pull them together and make them SEAL Team 6 on whatever particular problem that you've got. But you could run into a problem where they might look at a problem and only look at it in the context of what we know, right? Quantum mechanics and general relativity, and they don't want to think about new things that could potentially be brought to bear. So there could be some flies in the ointment with that thought process. But that in some ways that does kind of exist in what we know as the Jasons, right? So and they do classified work all the time.
Interesting. So I guess the question is, where are the brightest minds in this particular area of innovation? Like if I was running the government and I wanted someone to work on some sort of top secret stuff like this, how would I even find the people?
That's a tough question to answer because
need experts.
Taking that question and going into like some specific steps you might take, right? What disciplines are relevant, right? And that's a difficult question to answer because there's so much stuff that we don't know. You probably would have to sample from a number of different disciplines, right? Both in general relativity and quantum mechanics, with some hope that maybe you've got the right sprinkling of ingredients to bring to bear to that. And then there is a history of, I think, some folks in academia that actually like to think about advanced power and propulsion that are also just primarily physicists in their day-to-day capacity, right? Hal Puthoff, although he's got a lot of many and varied interests, he's a great physicist. He's published a lot of great papers in the literature just thinking about physics, right? He's got some stuff he's looked at called the polarizable vacuum. And so, in my drawer of preferred papers, I have a number of papers in there that are from Hal's work on the polarizable vacuum because I find that interesting and fascinating. And so there may be some things out there that are adjacent to the concept where you could try and pull some of that together, I guess.
That's a fascinating thing for you to say because Hal believes they have them. And he believes that we have 10 of them.
Yeah. Oh, yes, I know that. Yeah.
Yeah, which is just so nuts.
Yeah.
And then, he's a little agnostic on the Bob Lazar story.
Mm-hmm.
But the Bob Lazar story, which I'm sure you're aware of, is essentially what we're talking about. Like, you would bring in some out-of-the-box thinkers. And if you found some wildly intelligent young scientist who put a rocket engine in the back of a Honda, which is what he did, you would go, what is that crazy fucker up to? Like, let's have him look at it. What's it hurt?
Right.
The guys
right.
at Rocketdyne say he's a wizard.
Right.
Bring him
Right.
out there. Or the guys at wherever he wasn't at Rocketdyne. He was at Los Alamos. The guys at Los Alamos said he's a wizard. So let's bring him out here. Let's see what's going on.
Yeah, his story is I'm not too familiar with it. Right.
It's the nuttiest story of all time.
Yeah.
And he supposedly, they denied that he ever worked at Los Alamos, but then they found him on an employee log. And not only that, he knew the outline of the place. He knew the security people. George Knapp took him on a tour of it, and he knew everybody. He knew the people that worked there. He knew how to get around. Like, he clearly worked there. So that's interesting that they tried to deny that he ever worked there. And then from there, he gets this job where he is flown out to the desert to Area 51 Site 4. And this is allegedly, right? During this time, he can't even tell his wife what he's doing. So his wife thinks he's going having affairs. He's got to leave and fly away at 11 p.m. at night. Like, right, buddy. You can't tell me where you're going? You want to work? Right.
Yeah, you're working late again?
The wife starts having an affair. And because of his
This
clearance...
almost sounds like a movie, right?
It does sound like a movie, which is one of the beautiful things about reality. Is that reality seems so fake that sometimes actual true stories are bizarrely fictional.
Right.
So his wife starts having an affair. Because of his clearance, he cannot be working on these things if he could be under extreme emotional duress. So they fire him. They tell him he can't. They don't give him any explanation. They don't tell him his wife's cheating on him. He starts taking people out to the desert, explaining to them, you have to see what we're working on. They fly this thing on certain nights, and they do these test flights around the base. It's nuts. So he takes these people into this area. They see it. They get arrested. When he gets arrested, he gets caught there. He explains what he was doing. He says, okay, I've got to go public or they're going to kill me. So he goes public with George Knapp. Initially, they hide his face, and then he says, you know what, fuck that. Let's just film me. Let me tell you everything. He goes over the diagram of this device, and he calls it the sport model, and it looks like that. That thing that we have right there.
It's almost like a hubcap, right? But
exactly.
Gotcha.
That's a copy of it.
Okay.
In the middle of that thing is some sort of a generator that he said works on this unknown element, this element 115.
Oh, some of this is coming back to me. I think I've seen some stuff over the years.
Yes.
Yeah, some of it's coming back to me now.
And essentially the way he describes it traveling, and again, this is in the 1980s, the way he describes it traveling is exactly the way you describe that sort of warp drive, changing space and time around it. And that you would point that thing where you wanted to go, and it would just...
Yeah. That it all sounds very surreal, right? There's another story. Again, as I said, I have a number of friends that are keenly interested in this, and so I've been exposed to some of the different things. And that to me, the Tic Tac account is interesting because it's got a lot of rigorous data, if you will, that helps you go, well, I can't explain that. I can't explain that. I can't explain that. There is another accounting that I just put in the category, my brain doesn't even know what to make of it, and it's the concept of Rendlesham Forest. I don't know if that rings a bell. There's something over in the UK where there's a base over there, and some airmen came across some very weird. I can't even begin to describe.
I'm not sure if I know this one.
It's pretty bizarre. I don't know it well enough to unpack it today, other than to say it's so bizarre that when you listen to the accounts that were recorded, right, it doesn't make any sense. It's like, if you think about if you watch an octopus in an aquarium, right, and the octopus is doing something, you can sometimes understand what their motivation is. There's like a cross-species ability to it's like communication but without words, right? That octopus wants to go eat that little crab or whatever the case may be. And so our chemical computers, even though they're different, we can look at their behavior and we can go, all right, I think I understand what that octopus might be wanting to do today, or a shark or a dog or a porpoise. But when you hear what happened in that Rendlesham Forest thing, it breaks all of my guessing machine, and I it's like,
What is the story?
a colonel and some airmen reported some weird stuff that was going on in Rendlesham
Jamie's got it
Forest.
here.
Yeah, and they went out and tried to investigate it, and they saw some. Again, I'm doing such a terrible job of summarizing it because I don't really know the lore very well. But
Here it is right here. We can
everything
read
they
it.
saw was very bizarre and crazy looking.
We can read it.
Right?
It
So-
says 40 years ago, a remote forest in Suffolk was the scene of one of the most famous purported UFO sightings in history. So just what did happen, and will we ever know for sure? Victor Thurnkettle was out chopping wood one morning in Rendlesham Forest in late December 1980 when a car drew up. Out stepped two men, aged about 30, dressed in suits. "Good morning. Do you mind if we ask you some questions?" asked one in a well-spoken English accent. Earlier, on 26 and 28 of December, United States Air Force security personnel stationed at nearby RAF Woodbridge had reported seeing strange lights in the surrounding forest. Forestry worker Mr. Thurnkettle, unannounced and unidentified visitors, asked if he had been out the previous night. I said no, he recalls. They said, "Did you leave the house at all? Did you see anything?" I said, "What?" They said, "Oh, there's a report of some red lights in the forest. We're just checking." And the two men, very politely but firmly, asked me probably about 20 questions. I thought they were journalists. They suddenly said, "Oh, well, fair enough. There's probably nothing in it," and left. So I bought the papers every day for the next few days to find out what was going on. And of course, there was nothing. 3 years later, however, sightings made the News of the World front page story. It proclaimed UFO lands in Suffolk, and that's official. The story was based on a memo from RAF Woodbridge Deputy Base Commander Lieutenant Colonel Charles Halt to the Ministry of Defense. It was released by the U.S. government, described as an encounter with an apparent UFO in the forest. Since then, the sightings have been the source of much debate and speculation among UFO enthusiasts and the subject of numerous books, articles, and TV programs. In March, a documentary concluded the sightings had achieved legend status like the Loch Ness or King Arthur. The forest even has its own official UFO trail, complete with a life-size replica. Go back up. Of the flying saucer. And this is the replica with like the Hamza thing on it, that hand thing. Bizarre. Thurnkettle, UK authorities have said they didn't learn about the incident. Okay, but what is the story, though? Let's get to, what is the story? Scroll down more. What does it say?
Yeah, and that gets into the stuff that it doesn't make sense in terms of what they describe the UFO doing. It's just very peculiar, right? So,
yeah, they got there. My heart absolutely plummeted. There was nothing. It was an absolute normal glade in the forest with 3 rabbit scrapes. They're all carefully marked. It happened to be roughly a triangle. Okay, what else does it say? What is the sighting? Burn marks on trees, but what's the sighting?
I can show you what the UFO looked like, but
Okay.
I mean,
Sure. That's what they said it looked like?
Yeah.
Whoa. And it had those markings on it?
I Googled it. My Google search said that Grush brought it up when he was on here, but I couldn't find even clips about it, so I don't know that we went that deep into it.
How bizarre is it that it has that symbol? What is that? That's an ancient Hindu symbol, correct? That Hamza symbol?
I don't know.
These are different symbols.
Oh, they're different.
Yeah.
That looks very weird. Huh. So what about this one stands out to you?
I put this one in the category of I don't understand if it's a real account, right? I mean, I think when you have a lieutenant colonel that's reporting something as factual, I tend not to just immediately dismiss it.
Right.
But and it's not just him; it's several people around him. What they described, right, doesn't make sense to me, right?
Mm-hmm.
You know, in terms of the David Fravor talking about the Tic Tac, I can kind of, that's not totally alien to me. I could, it's trying to maneuver with the aircraft and it's maneuvering to their cap or whatever the case may be. And I can kind of connect the dots with that. But the Rendlesham Forest thing, it doesn't make any sense to me.
Well, what about it doesn't make any sense?
What they saw, why it was doing what it was doing.
What was it doing?
It just was out in the woods. It was out in the woods, with blinky lights and doing weird stuff. And I'm like,
Why is that weirder than the Tic Tac to you?
I don't know. So this is a gut thing, right? In terms of my gut's telling me I don't understand this. This doesn't make sense to me. I don't know how to explain it any better than that. So,
but if it's just an object that's in the wood, blinking lights, and looks like it's flying, why? I just don't understand why that's weirder than.
I think they also described it had like melty bits or something like that were like dripping off of it and so forth. And it sounds so completely surreal. I think maybe what I'm unconsciously trying to do is I'm trying to, map. How might I map, math and physics to what it is that they're describing to me? And I just,
Jamie, is this the one where they found debris at the scene? Did someone brought this up? Was it Jacques Vallée that brought this up?
Here it said, a piece of debris is seen burning up as a fireball over England. Servicemen thought it was a downed craft. Holt's memo says glowing object, metallic in appearance, colored lights.
Attempt to approach the object. It appeared to move through the trees, and the animals on a nearby farm went into a frenzy. One of the servicemen, Sergeant Jim Peniston, later claimed to have encountered a craft of unknown origin while in the forest, although there was no published mention of this at the time, and there is no corroboration from other witnesses.
Yeah, so there's no matter how far you dig, there's not going to be very much satisfactory resolution of the mystery, if you will. It's just a bonkers kind of story.
This one stand out to you more than, like, say, Roswell? Because Roswell, to me, is one of the most bizarre ones. When you look at the front page of the Roswell Daily Record, I believe, that has this story saying that the government has recovered a flying saucer, and that a crashed flying saucer was found. And, the story is that they grabbed the wreckage and flew it out the Wright-Patterson Air Force Base in two separate planes in case one of them crashed, and Truman met them there. Like,
maybe in that case, it's it's a potentially a purported spaceship, and it was around military bases. I don't know.
It's just the weirder.
Again, we're getting into the fact I don't have a lot of depth in some of these areas, right? So
I understand. But it's just the weirdest aspect of this whole crashed retrieval program, the alleged crash retrieval program. Like, if it has occurred, and it really does go back to the 1940s, like, how did you guys hide this? Like, how have you kept this secret so long? Is that even that's conceivably possible?
That's one of the things I wonder about. There's a book I was recommended to read called Blind Man's Bluff. And it's a book about deeply classified projects connected to the Navy, right? They were, I think the end effect of what they were trying to achieve as part of what's detailed in this book is you remember hearing about deep sea rescue vehicles, right? So deep sea rescue vehicles, basically that was a cover for some submarines that the Navy was using to put listening systems on communication cables that were at the bottom of some of the bodies of water that I think the Soviet Union was using at the time. And so this book kind of details a number of programs that went through and developed kit and hardware to go through and accomplish these different tasks. And so it's neat to kind of, see how black programs like that unfold. I don't know how that book got published, but it's a fascinating book. But then that speaks to what you're wrestling with, right? How do you have something that's so classified that doesn't leak, right? Because all the other data that we see from other programs, there you can keep a secret for a little while, but you can't keep it for that long. Right. At least that's when I look at these other things, that's what comes to my mind right now. That doesn't mean I'm right. There could definitely be programs that are out there, right, that are maybe they've figured out how to get around that. But when you look at some of the most classified military things that are out there, they usually have a lifetime associated with
Maybe
them.
it's just one of those things the government's really good at. Like, the government's really bad at a lot of things, but maybe they're really good at that. It's just that one thing, they've got it down.
Right. Or at least there's a small section of the government that's really good at that, right?
Well, Hal's speculation, when Hal says that he's pretty sure that there's 10 of them, that gives me pause. because that's a very serious person.
Well, yeah, he's a very discriminating individual,
Yes.
right? He likes to question everything,
Yeah.
and even though he's thought about some very interesting things over the span of his career, right? He does bring a little bit of that squinty-eyed physicist to some of the different things, and so that gives you some measure of comfort that even though he's thought about some wide-ranging things, he's bringing a little bit of that skepticism to whatever he's been confronted with.
Also,
right? So,
as crazy as what he says is, there's some things that he won't talk about. Which okay, what is that? Like, if you're telling me there's 10 crashed UFOs of non-human intelligence, and then there's stuff you can't tell me,
Right.
that
Right.
makes me just go, what else? What have you seen, Hal? Stop bullshit. You're 88 years old. Let's go.
Yeah, right. You're on the
Spill
clock,
beans.
bud. You're on the clock.
Spill
Come
the
on.
beans, buddy.
Right.
Come on,
Right.
if anybody knows, please. But I guess if you did spill the beans, my goodness, you would no longer have access to any of that stuff, and you'd probably be in trouble. They'd probably immediately you'd get audited.
Yeah. Oh, yeah. Absolutely. You'd have a lot of special things that would happen.
A lot of bad things would go your way, I would imagine.
Yeah.
Because you're what he describes, that put it in light and perspective to me. He said you have to understand that one of the things that would happen is there would be real problems because you'd have to figure out how this stuff was funded. So this is funded by misallocation of finances, so you lied to Congress. So these are crimes.
Right.
These are crimes that put people in prison for life.
Yeah.
And then on top of that,
But by the way, that goes back to that book I was telling you about, Blind Man's Bluff, because it talks about the amount of money that went into that program. That was hundreds of millions of dollars.
Right.
Right. And it's interesting. That gives you like a little bit of a window of insight into how the black classified world moves stuff around. Right.
Right.
So,
and then you also have this national security problem, because what Hal's saying is that we're not the only ones that have these things, and that there's essentially a mad race to try to back engineer these things and to successfully complete. And this was the real fear, like when people were seeing the New Jersey drones amongst conspiracy theorists. I was like, oh my God, what if China's already nailed it?
Right.
And they're buzzing us.
I gotta think when you look at any of the counts of these things, the important things to maybe help categorize the nature of things that they see. If a craft has the ability to manifest extremely fast speeds, SR-71 does Mach 3.2. If you've got something that has radar track data that shows it's doing Mach 8 or Mach 10, that's interesting. Now, we do have hypersonic stuff, so you can't just automatically say that it's something exotic. It still could be something that we know might exist out there with some other flags on the side of the vehicle. But then, like you talked about G-forces, if it can do like a Tron turn, right, that 90-degree kind of turn, and you got a radar track, that might help you categorize the nature of the different signals that are out there. So, and to me, that's why like the Tic Tac thing has always been something that's hard for me to just sweep away because of the quality of the data. And some of the stuff they describe, I can't imagine other conventional systems that could potentially explain what they're seeing. But a lot of the other stuff I can actually probably piece together in my head. It could be this or it could be that, right? They talk about the cubes inside of a clear sphere. There are patents in the system for radar corner cubes that are a cube, a metallic cube inside of a clear balloon that gets floated to evaluate radar sensitivity, right? And so
What do those look like?
it just looks like there's a patent in the system. So it's a corner cube, but there's a patent that has a version of that that's light enough to go inside of a some kind of a balloon. Maybe it's filled with helium or something like that. There you go. That's the patent, right? So there's a patent in the system, and so I can certainly see maybe if that's tethered to a boat, right? They're just evaluating our radar systems, if you will. And so,
well, that would kind of make sense until you listen to Ryan Graves' depictions of what these things were doing. That they were standing motionless at 120 knot winds. They're moving at insane rates of speed.
If it's tethered, if it's moving, I can't describe that. But if it's static, it could be tethered to a boat.
Right, but that looks goofy. Like if you look at what that looked like, Jamie, pull that photo off you just had. Like that, I don't think that's tricking. A fighter jet
the
pilot.
one on the left though is it's actually a metallic cube inside.
Interesting.
So
The one on the left. Is there an image of that with the metallic cube inside the sphere?
Just be the patent. I don't know.
Just
That
a
would be
patent.
Like
Okay, so it's theoretical.
They don't want us to know how it works.
Right, of course.
So in a lot of cases, I can again, I'm agnostic, and so I bring this framework to the
Right.
table, and so only the Tic Tac one's really, I think, the one that bubbles up in my mind with the highest quality data that I haven't been able to categorize. Well, it could be A, B, or C. That's
back to that.
a more
I saw it too.
boring explanation.
Jamie, go back to that blue.
I
Click
wanted
on
to
that.
explore. It could be some fake AI.
Could be
thing someone
nonsense.
made up.
Pilot's notes for cube transmedium vehicle.
Yeah, it doesn't sound.
Yeah,
promulgated by
that's-
order of air
That's got to
control.
be
It's like
AI.
some nonsense.
So restricted. Come on, it's restricted. This is like super important.
It says for official use only.
This is
right?
on the internet. It's gotta be legit.
Yeah.
It's
Def-
just, yeah.
I am
Like,
I am a
you could
French.
buy a
the
mug.
Tic Tac.
I am a French model, right?
Yeah.
It's just to buy stuff. On
Oh,
the
it's just to
website.
buy
Yeah,
stuff.
yeah,
It's just goofy. It's
yeah.
just silly. We need to get those. Get some
Yeah.
Tic Tac stuff.
But
But the lack of sonic boom is one of the things that I want to talk about.
Yeah.
Like if that thing could move at that kind of a hypersonic speed, there would
Right.
be some sort of a sonic boom.
Right. If it's not exactly right, if it's not some kind of laser system that's creating pixels,
Right.
right, and it's some solid thing, if it's going supersonic, it's based on everything we know with aerodynamics, it should have a sonic boom. And if it doesn't, and it is a physical thing, then that demands an explanation, right? And I wouldn't be able to explain that, right? And so that
Right.
that's exactly why something like the data that comes out of the Tic Tac thing, I haven't been able to just pound flat and make go away, right?
Right.
It keeps surviving all of my grumpy physicist attacks, right? So,
Does it frustrate you that you've never seen one of these things, or have you?
so funny story, and beer is involved.
Uh-oh. How much?
A
Were
little
you
bit.
drinking with Shane Gillis?
A little
How
bit.
much beer?
A little bit. So we were down at Kennedy Space Center, and this is a cautionary tale to don't always believe what your eyes see, right? Because you potentially could lead yourself down the wrong path. So we're down at Kennedy Space Center. We had put some docking cameras on some space station modules and spent a lot of, number of days working long hours wearing those uncomfortable bunny suits and so forth. And so finished all this stuff, wanted to go celebrate. So we went to the beach and had a little bit of unwinding time and drank a few beers, hanging out. And so we're out on the East Coast down there close to Kennedy. And we're looking up at the sky, and you could see some of the satellites coming over, right? Your eyes adjusted to the light. You could occasionally see some satellites coming over, and you kind of expect them to have a track that goes, west to east, if you will. Generally, I mean, they can come to all different angles. But then we started seeing some satellite tracks that were very different from what we might expect. Being rocket scientists, right? We're watching this stuff, and that looks a little different. That's kind of interesting. And it's at a very different angle. Well, maybe it's a Russian spy satellite that's retrograde, and it's, we're trying to figure out what this could be. And then, a couple more beers later, and, we see 4 or 5 more of these tracks, right? And we're like, well, maybe all these people that talk about these crazy things, right? Maybe there's something to that, right? Now, there's about an hour's gone by as we've gone through this process, and we finally see another one of these little glowy orbs, if you will. And I look at it, and I just realize out of the edge of the glowy orb, the wings of a seagull. Right, so it's the white belly of a seagull reflecting the light from the nearby city, and so that's what we're seeing, right? And so that's one of those things that's just something to make you think about what you're seeing. It may not be, I mean, because it's breaking all my guessing machines. It's breaking all of our guessing machines, and we're wondering and speculating about it, but. In the end, it was just, it was just a seagull doing their nightly business, right? Look at these silly guys looking at me, right? So,
That's funny. That is funny.
So yeah, that's my only experience.
Yeah, well,
right?
the mind definitely plays tricks on you, especially when beer's involved.
Right.
But
right.
I can't dismiss all of the different, very serious people that have talked about these things, and that's where I get really perplexed, and my agnosticism gets tested.
Right. I tend to try and always keep a squinty eye towards it, and I think that's probably good to do that, because then the stuff that survives that filter, right, is high quality stuff, right? And so the things that keep coming out of the Tic Tac thing, I can't kill that. I keep wanting to try and kill it, but I can't.
What about when you look
kill
at
it.
things like the Go Fast video or the FLIR video, and you look at these crafts that are moving in some very weird way that they don't exhibit traditional propulsion signatures.
So, yes, those are interesting videos, and they come from trained professional fighter.
Pull up the one where it rotates, Jamie.
Fighter pilots, and so I can't dismiss those accounts. But the integrated quality of that data is not the same as the Tic Tac,
right?
Where you've got multiple aircraft, multiple radar systems over multiple days. Right, that's one of those.
And eyewitnesses.
Yes, exactly.
Yeah.
And not only eyewitnesses. I mean, they're laying eyes on this thing, and it's not just one plane. Where sometimes you can fool yourself.
This thing is this is the gimbal video. This thing's very strange.
Right.
Put the guys talking about it because
they're all going against the wind. The wind's 120 knots from the west. Look at that thing, dude. That's not our LNS though, is it? It's not. That is the LNS, dude. Well, if there's like... Look at that thing! It's rotating.
It's rotating. It's going against the wind and it's rotating.
And I acknowledge the fact it doesn't have any thermal signatures that were indicative of like a plume or something like that, right? So some of those things definitely are hard to explain.
It's also listening to these guys, listening to fighter pilots, going, "Look at that thing."
Yeah, because their eyes are trained to go through and discern different things. Because they're always thinking about, can this kill me? Can I kill it? What do I need? I completely acknowledge the fact they have that framework drilled into their head, and that helps put this into a special category. But those are unfortunately single data points, so I can't do anything with that, right? And that gets back to what we talked about at the beginning of all this. I would love for somebody to show up with a notebook, right, full of all these great observations that would help me. We're making these little nano chips that we're trying to use to extract energy.
Can I see those?
Yeah, sure.
Is that the actual nano chips?
These are a bunch of the nano chips that we're doing. This is part of the Casimir company that we spun out. These chips interact with the quantum field and generate a voltage potential between those leads. And so we measure voltage on those guys when we put them in dark RF shielded enclosures. There's some pictures.
That's so cool.
And so
looking at these is so cool.
Yeah, and it's fun to think about how do you even make stuff like that. We can talk about that in just a minute, but let's talk about some of the applications, right? This is let's see. Can we go back a couple slides? Keep going. One more. All right, so let's just spend maybe 3 minutes here talking about the Casimir force, at least picking up where we left off.
Okay.
Right. So we talked about the idea of the Casimir force is a macroscopic observational consequence of something called the quantum vacuum, these fluctuating fields and forces. If you go to the next slide, Jamie. So conceptually, the following is true, independent of anything that we're doing with the nanotechnology we're developing. If you allow the quantum field to interact on these two metal plates that we talked about as part of the Casimir force, it will apply a force over a distance, and it will cause that gap to close and go to zero, right? So that is, by definition, a force over a distance, and so that is a unit of work. So the Casimir force phenomena is a illustration of extracting energy from the quantum field. So independent of anything that we're doing, right, that's part of what's baked into the idea of the Casimir force interacting with the quantum field. Now, you might say, well, maybe we could use that as a power source. The only problem with this textbook illustration of a Casimir cavity is once the plates have collapsed, right, there's no more. You can't get any more energy out of it. You have to actually pull the plates apart. You have to wind the watch again, if you will. And so this type of an approach would at best simply be a battery. So you couldn't extract continuous energy from the quantum field from this type of an apparatus. So this leads into an innovation that we came across. So Jamie, if you go forward one more slide. This is a slightly larger version of that scanning electron microscope image. So we've changed the standard Casimir cavity concept by adding these pillars along the midplane. So we have these structures that we put inside the middle of the Casimir cavity. And so you see we've got a cavity wall on the left and a cavity wall on the right, and these big 3 pillars. The walls are fixed to the substrate. They can't move. We don't want them to move. We want them to stay still. And then the pillars are also fixed to the substrate. They cannot move. The walls are electrically connected to one another, and the pillars are electrically connected to one another, but they're isolated. So that's just a physical description of what this is. So now let's talk about how does this custom structure interact with the quantum field? What's the difference with this particular structure? So for that, let me give you a metaphor. Imagine a Pacific atoll island out in the middle of the Pacific Ocean. It's surrounded by the Pacific Ocean with all this random wave energy that's beating the outside of the atoll island. But at the center of the atoll island, there's a nice lagoon, right? Very quiescent, very smooth. The water's connected to the Pacific, but a lot of that wave energy can't manifest on the lagoon. So it's a protected and nice environment. So imagine, Joe, you're sipping, some nice water and having a nice paddleboard day, quiescent, enjoying yourself. And, Jamie, he took the other package and he went deep sea fishing out on the Pacific Ocean. And so he's really bobbling back and forth, and it's much more uncomfortable for him. Maybe he's getting sick and feeding the fish, right? So now with that metaphor in mind, let's come back to the structure. So this structure, the walls on the outside are like the Pacific atoll island. Inside the quantum field, which is like the Pacific Ocean. So it's assaulting that structure on all sides. The pillars are like you on your paddleboard in the lagoon. It's a protected environment. And so the way the quantum field interacts with this structure is it will occasionally cause a real electron inside the walls to quantum tunnel to the pillars. And so the pillars are like you on your paddleboard. It's a very quiescent environment. And so the electron shows up through this quantum tunneling process, but there's no wave energy on the lagoon to mirror that current back to the walls. So in that way, this structure will interact with the quantum field and generate a voltage potential. So we can measure a negative voltage on the pillars relative to the wall. And so although this is a very tiny little cavity, and we can measure the voltage directly using atomic force microscopes, if we put these guys together by the tens of thousands or hundreds of thousands, then we can get to voltage and current levels that map to things that we care about in application, like a tire pressure monitor system, something that uses microwatts worth of power, or a Fitbit, or you've got the ring there. I think that's an electronic ring or something like that.
Like an Aura ring.
Yeah, some low power applications. And so using this this approach, we're trying to create chips that are about the size of your pinky nail that generate 1.5 volts and 25 microamps. And so that maps to a number of chips that are on the market today that operate at that power level, but they have to be recharged. We don't have to be recharged. So we're like a solar panel that works in the dark. So you can put us in your device, and then it can go down to the bottom of the ocean, and it will continue to work. Or we can give it to our buddies at Intuitive Machines, and they can carry it to the surface of the moon, and maybe they want to throw a sensor off to go measure something, and it'll collect data, even though the sun stops shining. So the cool thing is, like I said at the beginning of this interview, we were going down this whole path of trying to understand the nature of the quantum field because we were motivated by where we might envision it could lead one day. Maybe we could add a deeper understanding of that physics Venn diagram and get to a point where we can figure out what do we need to put into the rings that go around that IXS Enterprise concept shift, if you will. And so it's cool to think that, maybe we could come up with a technology that, provides useful power today for things like this. Maybe, if we put it in aggregate, if we put a lot of them together, right, we could get to a point where.
What is that chip?
This is just a 3D print of having a bunch of of those little chips that are 5 millimeters by 5 millimeters, 1.5 volts, 25 microamps. If we add a bunch of those together at a very large extreme, that particular board might generate 3.4 watts. And so that board could recharge your phone in 3 hours. And so imagine a scenario where you had a phone that's pretty resilient, that for the most parts, you'd never have to plug it in. That might be pretty useful, right? So, and it's neat to think that pursuing, this whole reaching for the stars type of thing has fueled this exploration of pushing the boundaries of what we know, and then kind of coming across instantiations that make us go, hey, wait a minute, although we were thinking about these kinds of things, look at what we could potentially do now. And so we could find ways to, feed the research and still bring value here in incredible ways. I mean, this capability is amazing to think in terms of what it could unlock, right? Especially if we could, if this is 3.5 watts, you could imagine you put a bunch of these together, you could rapidly get to a kilowatt or even more, right? And have expeditionary power. I don't know if you've ever wanted to have a farm out in the middle of some untouched area where you didn't want to pay the money to run the power line. Well, now maybe, in 10, 15 years, maybe you wouldn't have to. We could provide a solution that would allow you to come off the grid, right? So,
I was seeing something online about some new technology that I believe was invented in Japan, where they have figured out a way to extract far more energy from solar panels.
Yeah, I think they've increased the efficiency on solar panels, but there is a limit to that, right? In terms of I think it's when you get to close to 40% efficiency on a solar panel, you're kind of at the limit of what you can do. And then the challenge you have with a solar panel is at the surface of the Earth during ideal peak lighting conditions, the flux of power you get is about 1,000 watts per square meter, right? So if you wanted, a system that provided 5 kilowatts of power, you could do the math and figure you need a fairly big area. With our technology, we can stack it on top of one another. We don't have to stretch out like that. And so the quantum field could potentially provide a lot more power with a much smaller footprint, if you will. Right now, I have to acknowledge we're still very early, right? We're very low power levels, and so we want to crawl, walk, run. But we're thinking about what can we do now to provide use, right? And then use those applications to continue to grow the capability at Casimir. So.
And then ultimately, if you have those things stacked 50 feet thick and, 700 meters in a circle, then you have enough power to make a warp drive.
Right. Well, and so this gets into the cool thing is what we're trying to understand and study inside these little chips that we're making is we're trying to understand the nature of the quantum field, right? The structure to the quantum field. How can we alter it? How can we tweak it? What can we do with it? Because we talked about the fact that negative vacuum energy density is potentially a good proxy for the idea of exotic matter in terms of what general relativity requires. And so in the process of developing a deeper understanding of the quantum field with what we're doing with these devices, right? I would contend that we're actually adding another circle on that Venn diagram that's potentially not only overlapping part of quantum mechanics, but it's also overlapping part of general relativity. And I think that's kind of what's going to be necessary to be able to make the idea of space warp real one day. We're going to have that new body of physics, those new E equals mc squared equations, right, that allows us to potentially, hey, if I do this and this and this, then it might, maybe I could solve that problem. But I think your instincts are right on, right, from the standpoint what we're doing in the micro here, right? If you cracked open one of the access panels on the IXS Enterprise and you looked, you might see some stuff that's like, I can see how these guys are descendants to what gets put together in that ring in macroscopic, whatever that might be. Right, so.
It's got to be so frustrating that this has this immense potential, but imagine seeing it. Like, how do you get to do it? I don't want to say frustrating, challenging, exciting. Just knowing that there's this potential energy source that can be tapped, and knowing that just like all technology. I mean, if you go back to the Apollo program, the amount of power that you have in your phone far exceeds what they used, and they had like a whole giant room filled with supercomputers, and now you just carry it around and you plug it into the wall, and it's 50% charged in 20 minutes. You know, it's like nuts.
Yeah, we take that for granted. It's interesting you mentioned that, right? If you look back through if you think about the Industrial Revolution, when we came up with steam power, right, and then when we later figured out gasoline engines. Right, the amount of power we had available to us changed so drastically, right? The change that it had on human civilization and human culture is just hard to fully comprehend. Because, I mean, if you think about all the different things that get done, a single tractor with one person on it will, do all the stuff that's necessary to seed a field, to cultivate a field, to plow a field. And it's amazing to think that that's possible just with one human being at the helm of the tractor. But you had to unlock all the energy, the insights to unlock the energy in what we know from petrochemical, right? Just gas, diesel, whatever, right? And so, it's neat to think how things like that change civilization. And so, in some ways, it's like if you think about the long-term benefits of reducing something like this to practice, right? We talk about the grid, right? You were here in Texas, and I think we had some issues during a very cold winter where ERCOT got its R removed, right? The power grid had some issues because it got really cold. But imagine a future where we can start to create microgrids. Maybe even eventually move away from something like that. And then what would that kind of a capability do for parts of the world that currently don't have any infrastructure in place? Right. There's a lot of places in Africa where if you brought this type of a capability where you could plop a brick down on the table that's 1 kilowatt, right, and let people know can you make use of this? And so just like Starlink provides this opportunity for people in remote locations to have access to the internet, right? We could potentially bring a solution to the table that could help a lot of places on the planet that they might not ever see that otherwise, right? So that's the thing. So those are some things that have us excited about as we continue to wrestle with technology, right? And anytime you're trying to do something, when you're trying to establish order where there's only chaos, it's hard, right? But the things that help us weather that is the long-term implications of what we're doing, both in the near term and in the far term. It's really cool to think, right? We can provide benefits, here, and then farther down the line here, and then farther down the line to here, and then, oh, by the way, the whole reason we're doing all this stuff is because we hope to try and make the idea of a space work possible one day, right? It's cool to kind of have that connection between all these different nodes along the way. Right? Or
you can see the path.
Yeah, you can see the path. Right?
You can see how it'd be useful for people today.
Right. I mean, think about like when we have a hurricane that hits, right, and the power goes out. You're without power until they can get the power lines up, right? If you have capabilities like this, maybe 50 years in the future or something like that, right, where everybody just, they're off the grid, right? That changes the nature of how we contend with, disasters like that.
Right. So, and monopolizing resources. Right. That's the other issue. We'd no longer be dependent upon fossil fuels, or essentially everyone would be independent.
Right.
And then you could imagine as it scales up, it gets better and better, just like cell phones were initially these very large bricks that, remember from Wall Street? The guy had
Okay, yeah, sure. I can do dinner.
Cool. You had that big brick with you.
Yeah.
And now they're these little tiny things.
Yeah.
And so you could imagine how that would eventually get to a point where it's portable and anyone can have power everywhere you want to go.
Yeah. So some of the things we think about in terms of the roadmap for things, right? It may take us a little while before we could provide all the power that's necessary for like a Tesla. But we could imagine a scenario where, like, I'm gonna hold this little prop up again. We've got this 3.5 watt brick, 3.5 watt card. Maybe we put a bunch of them together to create a 1 kilowatt module of sorts. So maybe a Tesla's got 50 kilowatt hours worth of capacity in it. most of your daily driving that folks do is, to work and home. So it's maybe 50 miles to and 50 miles from, 100 miles a day, right? And so if you've got an electric vehicle that has all the batteries already in it, but then you make the decision to buy a 1 kilowatt Casimir module, right? And you connect it to your car. That module will provide, over a 24-hour period, it will provide 24 kilowatt hours of capacity. And so in terms of the driving duty that I just talked to you about, right, you're not going to drain the battery enough where the Casimir cell couldn't just continue to recharge it. So in that particular instance, even though we might be a little bit farther away from, being able to power a whole car, we might be able to find opportunities for early adopters where, hey, for 99% of how you might use your electric vehicle, you don't have to plug it in, right?
So from where we are now with your current research and all these incredible ideas, what steps have to be taken in order to advance this stuff? Right.
So the first step is trying to get to the power magnitude I just described, 1.5 volts and 25 microamps. So we have chips, these chips right here, they can achieve very high voltages, but then they relax to a certain steady state voltage over a long term, right? So they have the ability to provide steady state power, but it's like 30 millivolts with a steady state current. And so it's the current that we're currently working on right now. We're trying to get the current up to that 25 microamp ability right now. And so that's the stuff that we're doing. Every month we're trying to do another generation of chips to go through and work the material science and get that capacity to that level. So, and making chips that's tough. That is tough business. So it's been quite the slog. We've been doing this since 2020. The first chips we worked on took us, 18 months to make. And then we got the time down to 12 months. And then we got the time down to 7 months. And then we got, these guys down to, this was a 2-week sprint from the time we did the design to the time we got them in hand. But roughly we're anticipating we can make these generations once a month. So making chips is very different from, how we view the rest, like this wooden table, right? If you think about making something, you think about drills and saws and cutting holes and putting bolts in and so forth. But when you talk about making chips, it's an entirely different approach to how you make things. You make things with light, and you make things with plasma, right? This will be a good opportunity for me to use a little verbal description, and then you can grade me on how well I communicate this, right? Okay. So, how in concept, how do you make something smaller than what you can see with your eyeballs? So, ordinarily, when we want to look at something very small, we use a microscope, right? So we got this optical system we look through, and then we look at something. Maybe it's got a paramecium or whatever in it. Now, what we're looking at is very tiny, and we use optics to blow that up. And in some cases, instead of putting our eyes against the little viewports on the microscope, maybe we'll put an imager, a camera, on there, and we'll take the camera will collect the image and put it on a big screen, a big LCD screen. Now, if you think about that in reverse, what if let's say you're looking at our chips and you're seeing these squares and circles and tiny little different shapes and so forth, but it's projected on a big screen. Now imagine for a moment instead you go through in some CAD program and you draw squares and circles or whatever. Maybe you draw a picture of Jamie's head, right? And then you go through and you take that digital file you just created, and you kind of look at this whole process that I was talking about in reverse. And so instead of using a imager to collect the image, you use a projector to project the image back down through the optics, right? Where now you project some shape you want to manifest on a chip, right? But you can't see it you could look at it with your eyes, but you couldn't see it, right? But you're using this projection system through the microscope in reverse to put the image down on the chip. So now the next thing you do is you take let's say you got a silicon wafer, and then you go through and you apply something we call photoresist. It's like a really thick, almost like a honey type of consistent, little thinner than that, right? But you put some photoresist on the wafer, and then you spin it at really high RPM, and it spins that photoresist so that it's very thin, and you take that wafer with the photoresist and you expose it to the image you want to put onto it with ultraviolet light, right? And so that hardens part of that photoresist. And then you develop that wafer to remove all of the photoresist that was not exposed to the ultraviolet light. And then maybe you expose it to a plasma and you etch it. And so every place where there's no photoresist, it etches the surface. But where the photoresists survive because you exposed it with your ultraviolet light, you now have an image. So you could look at that with a microscope again, and then you'd see, Jamie's mug on the surface of the silicon wafer. And so in concept, that's how the idea of when you make a CPU or you make memory or you make any of this digital technology, that's technically how it works. Are you old enough to remember microfiche?
What is that?
The
little film?
The little acetate things in school that you put in, right? So,
So
that's another kind of illustration of it, but just not applied to a chip, right? So,
well, I would imagine the manufacturing of something like this is a spectacular undertaking that would require a long time to develop the kind of factories that you would need to do this kind of stuff at scale in the United States. And this is an issue that we have that was really highlighted by the COVID pandemic, where we weren't able to get shipments of things, and a lot of cars weren't for sale because they didn't have the chips to put in a lot of the new American vehicles.
Or in some cases, they took functionality out because they couldn't get the ding-dang chips to go do what they wanted to go do. I was really glad to see a lot of attention be brought to bear with, I think it was the CHIPS Act. Mm-hmm. And even Texas has taken a very strong stance on trying to try and attract some chip manufacturing capability here in Texas, right?
Yeah, we were talking about the Samsung plant that they built here.
Yeah.
But the Samsung plant kind of highlights the issues because they weren't able to achieve the tolerances that they required in large batches.
I think they'll eventually get there, right? Mm-hmm. Those are just illustrations of the fact it takes a while to get everything dialed in. Just like it took us 18 months to get our first chip, and then now we're getting a 2-week sprint. We can make our chip, but it took 5 years to get to that capability, if you will. I think they'll get all that figured out. But in my mind, the other value proposition for chip manufacturing, right, is, to me, chip manufacturing is like the 21st century automobile manufacturing jobs, if you will. It seems like that could provide a great opportunity for, people to get meaningful work that pays well, that makes a product that a lot of people need, right? And so I think in some ways that's the upside to trying to focus on getting more chip manufacturing here in the States, right? So I just think that's a win. That's a win-win, right?
Yeah, because the chip manufacturing, one of the things that Apple stated, they have apparently a big leap coming forward with the iPhone 17, and they think that they're going to have to manufacture these in China. I was reading Tim Cook talking about it, because they're saying that China is the only nation that's capable of achieving what they're trying to put into these.
Is it China or Taiwan?
I don't know. I believe it's China. I think,
because I certainly. Now, I don't know definitively either, right? But when I think of,
maybe it's just manufacturing that's the issue, not the chips.
Okay.
But see if you could find what Tim Cook said about needing to develop the iPhone or manufacture the iPhone 17, because I think a lot of their stuff they do in India now, but they think this new one is going to be so sophisticated that they're going to have it made back in China again.
Yeah. So when I think of cutting edge chip capability, I think of TSMC, that is. In Taiwan, right? And they've got those machines, the ASML machines that this is a very interesting thing, right? So the machines that help make some of those tiny chips that are inside the iPhone, they're made by this machine that's developed by a company called ASML over in the Netherlands. And part of me thinks it's like that's a very small brain trust of people, right, that are making machines that are kind of setting the pace for, because I think about what happens if somebody, a bus has an accident or something like that, right? Because it's just like such a small group of people that have this skill on how to make these tiny little features that are 2 or 3 nanometers. I mean, that's crazy small. What
percentage of the population can do that?
Right. There's not a lot, and 2 or 3 nanometers. It's like that's if you were to put DNA on the table, right, and you calculated 2 or 3 nanometers, it'd be as very. Oh, here, let me give you here's a better comparison. If you hold a marble in your hand, and you imagine that as 1 nanometer, right? It's just kind of a comparison here. Right, so you have a marble in your hand, that's 1 nanometer. Well, how big is a meter? A meter is the size of the Earth by comparison. So just to put a nanometer in mind, right? So we can all envision a meter, right? So that puts a nanometer to scale, right? And so they're making things with lateral features that have this handful of nanometers in mind. Now that said, I do think
that is so crazy.
I do think chips are reaching a limit in terms of what they can do for the lateral features. The next big chapter, I think, for chips is they're going to go 3D. They're going to start making them. They've got a bunch of efforts in place to try and figure out how to make chips much more 3D, like especially when they may even include multiple different chips, right, that serve different purposes, if you will. You'll no longer just have this single flat chip that does this surface. There'll be a bunch of chips on top of one another that get integrated into assembly. You already see it in this tire pressure monitor system. There's a little chip here on the back of that's actually a system of chips. There's a bunch of chips in that little silver piece on the end there. There's a microprocessor, there's a Bluetooth module, there's a pressure sensor, and then there's a receiver.
And look how small that is.
Yeah, that's nothing, right?
Tiny,
so that little shiny silver piece, that shiny silver piece, that's not only just the pressure sensor, it's all the other support electronics, and everything else is just simple dumb stuff.
And
if
a
you
big
will.
battery in comparison to everything else.
And a big battery that has to last 5 years, right? And so that's
nuts.
That's why they. This is not. You don't take the lid off this thing. This is glued on, right? When it's done, you just throw it away, right? So that's the current operating process.
So crazy. Now, when you think about the current capabilities of AI and how it's expanding at a very rapid rate, do you think that will assist us in being able to figure out new ways to accomplish these tasks?
I think. So when AI first came out, I tried it a few times, and I wasn't satisfied with the quality of what I was able to do with it. This is a number of years ago, right? But in the last 12 months, I've kind of gotten in the habit of using it much more in a lot of the different things that I do, and it certainly does bring a lot of value in certain areas. A lot of people talk about artificial intelligence is going to kill us. Oh my gosh, it's going to kill us, right? And I don't think it's artificial intelligence that's going to be a potential big problem. It's more a measure of artificial incompetence, right? And so let me unpack that.
Okay.
So I think AI is an amazing tool, and it's only going to get more useful as we continue to move forward. And I use it every single day, right? In terms of different things that I explore, it's extremely useful. And there's times when you're interacting with it where you might even think to yourself, all right, come on, is there some dude actually typing on the other side of the screen? Because it's like, it's joking with me, for crying out loud.
And it's instantaneous.
Right, and it's instantaneous, right?
Yeah.
And so I think as human beings, we tend to anthropomorphize everything, right? And so I think in a lot of ways, we want to give it more credit than it is due, right? And so when we interact with it, we might think based on the quality of the interaction, oh my gosh, this stuff is amazing. This is artificial general intelligence. But then it'll go off and do something totally boneheaded, and you'll even call it on it, and it'll say, no, I did this exactly right. And it's just like, and from your own training, right, that whatever it offered up is quite
not ready yet.
Quite wrong, right? And
not
so
ready for prime time.
I keep waiting for somebody. Do you remember the movie Dr. Strangelove?
Yes.
From the 60s, right?
Yeah.
So it's Stanley Kubrick thing, and this movie of absurdity showing how incompetence in the government and the military leads to the destruction of the world, if you will. It's like we need a Stanley Kubrick equivalent today to do a movie called AI Bob, right? Where AI Bob, accidentally takes out the world while trying to help, right? You know,
Right.
And it just, I think it's one of those things where I think AI is an amazing tool. We need to find out more ways to use it. It's incredible, but I think we just need to remind ourselves it's not quite as capable as we might think it is, and we need to be careful of that so that we don't, put it in control of something in a certain way where because it has these other faults, right? It does something that's really unfortunate, right?
So we have to make sure that it's reached a very high level of proficiency before it gets...
Right. Or just be careful about how we use it
Right.
and never be afraid to question what it provides, right? Because there's no question it helps me be faster at a lot of stuff I want to do, right? But I have a lot of skills and talent that I use to filter whatever it's given me, and I go, no, that's totally wrong, right? So...
But I wouldn't be able to do that. I would just trust it. And I'd build something that kills everybody. Yeah, that's...
dang it, I forgot to carry the 2. Right?
Well, when you think about the potential future versions of AI, that's where things get very interesting. Because if you do get to a point where it achieves a much higher level of understanding of all the physical properties of the universe and does really understand the quantum vacuum and does really understand how to utilize it.
So I think one of the things, because I have been thinking about this, is, and I know a lot of other people are trying to figure out how to use AI to go through and help navigate on physics frontiers. AI is trained on a bunch of existing data, right? And so in some ways it is an enormous experiment in statistics. And so... So I would wonder how much an AI system by itself could innovate new ideas. It certainly could recognize patterns.
But
Right?
once you institute sentience, and then if it's possible at all to make it creative,
That's where I wonder what. Great question, and I'm not an AI expert, so I'm going to tread very carefully here. When I think about how they train AI today, it is certainly a measure of statistics, right? And so when you talk about an AI agent being able to actually think in the way that you and I might consider thinking, I don't think anything that we have does that per se, right? You just got a bunch of GPUs that are taking an input and then passing it through a matrix of all this stuff that's from training, and then so the statistics of what comes out, right, is a result of whatever training that was done. So it's not like Leonardo da Vinci imagining where he's going to put his next brushstroke on the ceiling of the Sistine Chapel. But certainly it could potentially take an image of the Sistine Chapel and mix it with an image of some other modern art or whatever, and come up with some cool homogenization of things, right, and so forth. So I still think I think we need to better understand what is consciousness, right, before we can really even do that.
what do you think it is?
Oh, that's I
Have you? I know you thought about it. You think about everything.
Right. Yeah, I don't know. It's a good question. I would speculate, right? Maybe this comes down to the nature of the quantum field, the quantum vacuum. I think there are other forms of radiation, scalar field fluctuations with the quantum field that are beyond electromagnetic, like the lights in this room. That's electromagnetic radiation. Scalar fluctuations would potentially be a whole nother realm of radiation that we currently don't have any sensors to detect, right? But maybe biology uses those types of things. And so there are things inside cell structures called microtubules. I think Hal maybe even mentioned something about microtubules to you when he was here the other day. But cells have microtubule structures in them, and I think that may be connected to the idea of consciousness, although I don't have a enough formulated answer to be able to defend anything. So I'm treading very carefully because this is not my area of expertise. But
it's so fun to speculate.
It is fun to speculate, and maybe we can schedule another opportunity to come back and we can talk about consciousness, bring a couple other folks that are more cognizant than me.
I would love that.
Yeah,
You want to organize that?
Yeah,
Do you know who you would call?
I don't know yet. I'll think about. I'll have a think. I actually probably have a couple other cool ideas for cool things we can confab on. I think a lot of people would really enjoy learning and listening about.
Well,
right?
that would be a fantastic collaboration with people that have theories about consciousness, along with these theories, these quantum theories.
Yeah.
Fascinating stuff.
Yeah.
Harold, thank you so much.
Yeah.
So
No worries.
interesting, and I'm so happy that people like you are out there in the world working on this stuff, which I'm sure one day, when people look at the past and say, boy, look at those cave people, look what they're doing. You know what I'm saying? Because we would look at the Victorian people, or we would look at people from thousands of years ago. I think they'll look back at this going, wow, this is where it all started.
Yeah. This was the moment. Right?
So let's definitely do that. Let's definitely have another visit and bring in some people that will explore consciousness together.
Sounds good. I love it.
Thank you so much. Really appreciate it.
Hey, thank you, Joe, for having me.
Bye, everybody.
Yeah.